Hello, I'm Chris Carberry, CEO of Explore Mars. Welcome to the first Humans to Mars webinar, Life on Mars, What Are the Implications? I hope everybody is healthy and safe in these strange days. Like many other organizations, we're launching numerous online programs to educate, entertain, and inform people interested in Mars explorations. Thanks to all of you who were able to attend our first weekly virtual Drinks with Explore Mars. A fun time was had by all, and I hope you'll join us again next Tuesday. We're going to be doing them every Tuesday evening at 8 o'clock Eastern Daylight Time. Also, in partnership with our president, Janet Ivory, we're also hosting Janet Planet's online astronaut academy, weekdays at 10 o'clock a.m. Eastern Daylight Time. Students from around the world are taking part in this spectacular event, so you should check it out. And for today's panel, which is the first of the ongoing series of weekly webinars that will be running probably beyond the Humans to Mars Summit, but certainly up until the Humans to Mars Summit that's taking place on August 31st to September 1st at the National Academy of Sciences building. Of course, you can find information on that at exploremars.org. Our next webinar will take place on Thursday, April 9th at 4 p.m. Eastern Daylight Time, and will focus on managing isolation in space and on Earth during our current crisis. The panel will be moderated by television news personality Sonia Gavankar, and we'll have special guest Scott Kelly, the former NASA astronaut and author of Endurance, Dr. Susan Ip Jewell, president and co-founder of the Mars Academy, and John Hanasek, CEO and co-founder of Avatar Medic. Should be a great and timely panel. I'd also like to thank a few of our sponsors and partners of the upcoming Humans to Mars Summit, including Aerojet Rocketdyne, Lockheed Martin, Northrop Grumman, ULA, the National Institute of Aerospace, and the Science and Entertainment Exchange, and many others, all of whom will be highlighted frequently throughout this webinar series. Now, without any further rambling by me, I would like to introduce our moderator extraordinaire, the host of Planetary Radio, Matt Kaplan. Matt, welcome and thanks for leading our fascinating discussion today.
Oh, it is such an honor and a pleasure. Thank you very much, Chris. And Chris, I don't know if you mentioned, you are the founder and CEO of Explore Mars, which is the parent, the guiding hand for this event today. Explore Mars with the Humans to Mars Summit every year. That I so look forward to, and I sure look forward to the return of that wonderful gathering in Washington, D.C. But since we are all faced with these hopefully quite temporary necessities of making life go on from home, we are absolutely delighted. We are thrilled that all of you could join us for this first outing. I am with the Planetary Society, where I have hosted and produced Planetary Radio for the last 20 years. But we have had a wonderful time collaborating with our sister organization, Explore Mars, for a good part of that period. And are delighted to continue that today. And I bring you greetings and regards from our CEO, Bill Nye the Science Guy. Having said that, we should jump in because we have a lot to cover. I mean, it's as big as the red planet, our discussion today, and what we may find there. Let me set the stage for today's conversation with a hypothetical. We've jumped forward to 2024. A rover named Perseverance, that we'll be talking more about momentarily, has been rolling across Mars for 3 years. Another visitor from Earth, a more recent arrival, named Rosalind Franklin, has been pulling up samples from below the surface of Mars. NASA and the European Space Agency have just announced a joint press conference that is going to reveal images and other data indicating that we just may have found strong evidence of life. Will this news, as my boss Bill Nye likes to say, change everything? What do we do next, and how will it affect plans to send men and women to Mars? But I'm getting ahead of myself. So hold that thought for now as we meet the two very distinguished guests that will be joining me here. You can see them already, I hope, on your screens. I really can't think of anyone else I would rather have on board to talk about this topic, beginning with Dr. Penelope Boston. She is the Senior Advisor for Science Integration at NASA Ames Research Center in Silicon Valley. And Penny's personal expertise is the geomicrobiology of extreme Earth environments, especially caves and mines, and astrobiology. As a lifelong human space exploration advocate, she co-founded the Case for Mars conferences in the 1980s and 1990s. That makes her a founding member of the Mars Underground as well. She's a member of Explore Mars. She looks pretty great in a fake spacesuit. She earned her PhD in microbiology at the University of Colorado Boulder. She was till recently the director of the NASA Astrobiology Institute based at Ames, and is a former professor and chair of the Department of Earth and Environmental Science at the New Mexico Institute for Mining and Technology. Also, the former associate director of the National Cave and Karst Research Institute. Welcome, Penny.
Thank you. Great to be here.
Dr. Jim Green is the NASA chief scientist. He received his PhD in space physics from the University of Iowa in 1979 and has worked for NASA ever since. That included 12 years as the director of the Planetary Science Division at NASA headquarters. Under his leadership, more than a dozen planetary missions were successfully executed, including the Curiosity rover and InSight lander, both of which are still quite active and delivering great science on Mars. Jim is NASA's representative on the COSPAR Planetary Protection Panel, where planetary protection guidelines are created and agreed to internationally. COSPAR, that's the Committee on Space Research. In 1915, you're not that old, Jim. And in 2015, Jim coordinated NASA's involvement in one of my favorite movies, The Martian. Talk about infecting a planet. By the way, he also hosts the excellent NASA podcast called Gravity Assist. Welcome, Jim.
Thank you very much, Matt. I'm delighted to be here.
So let's back up a little bit and talk about the current status of exploration on Mars now and what's going to be happening there, well, in less than a year now with the arrival of this new rover. Tell us, what's the status of Perseverance?
Well, Matt, Perseverance is actually moving forward. It's all down at the Cape. And in fact, the radioisotope power system is already connected. It's checked out in many ways. It still has a number of things to do yet, but we're making great progress. So it is on track for a July 17th open window for us to be able to launch. And that's when that highway opens up for the next 3 weeks that can get us to Mars.
This is like almost everything NASA sends to around the solar system nowadays, an international effort, right?
It is, and indeed. And in fact, if you had my little graphic that shows Perseverance, this particular rover has got a fabulous set of instruments where we have participation from Spain on a weather system. We have Norway having a ground penetrating radar. We have the French working with us on some really great camera and laser systems. And we have an Italian retroreflector. But the whole point of this particular mission is really at the end of the arm. This is where we have high resolution images that we want to be able to really look at the rock record and then make decisions in terms of creating cores. It's got a core at the very end of it. And I have an example of one that I can show everyone what these cores look like. They're like a piece of chalk in size, or for those that are young enough that don't really understand what chalks and chalkboards were all about in their education, like a Crayola crayon, one of the large sizes. Once those cores are made, they're stuck indeed into an aluminum sleeve and then dropped on the surface for then later pick up and bring back. So by the end of that decade, the 2020s, we hope to be able to have these samples back in our BioLevel 4 facility and begin the process of really looking through them to determine their viability and allowing scientists to get access to them for further research. So we're doing great.
So, and even though she resembles her sister on Mars, Curiosity, You've given at least a couple of examples in that image, and with those cores especially, of the new capabilities that Perseverance is bringing to the red planet. Pretty powerful machine, isn't it?
Oh, it absolutely is. And the rock record is so important to us. You know, we know that Mars was a blue planet early on in its history. It went through rapid climate change. It was a blue planet during the time we know Earth had life started on it. And so maybe life started on Mars too. And so we're really quite excited about going there and interrogating that, being able to bring back those samples and look at them. You know, for all the minerals we have here on Earth, there are hundreds of minerals for which life is such a key part of that create those minerals. And so if we can find the right set of information, indeed that press conference you talked about would be really lively.
So sample return, you know, I often refer to it as the holy grail of robotic exploration of Mars, and could be for other places as well. I know you've got a slide about that as well.
Yes, I do. If we can bring that up. This was how we envision right now working with our international community to be able to get those samples back. And it all requires NASA landing a Mars ascent vehicle. This is shown on the surface already in this diagram to the left. We then have fetch rovers that pick up those samples that we laid on the ground and deliver those. That's in the bottom middle. And then on the right, we launch off of Mars, those samples in a container. And then that container goes into orbit, for which then an ESA satellite will come down using ion propulsion into low Mars orbit, pick those samples up, and then bring them back to Earth. So it's indeed a multinational effort, and the planning is going real well.
Penny, you're a longtime Martian. What's it going to mean to scientists like you to get those samples back here and into our nice big labs on Earth?
Well, you know, as you say, Matt, it's been a holy grail for many decades, and pretty much my whole career. I'm sure that's true for a lot of us. And the opportunity to actually get our lab facilities here on Earth to bring all of their power to bear on samples is a new step, really, in marching forward to be able to analyze Mars materials. The missions that we've had so far and the ones to come are magnificent. But, you know, there's only a certain amount that you can smash onto a spacecraft and a lander and a rover before you run out of power and mass and all of that. And so the ability to do these really in detail studies of the geochemistry, the mineralogy, the foundational bedrock materials, perhaps even some of the fine materials on Mars will give us insights into the climate history of that planet, which is very important to our understanding of climate in general on our own planet and beyond, and also potentially allow us to look at organic materials and various other things that may be significant for the potential history of any life that may have arisen on Mars.
Jim, I want to go back to you. I gave short shrift to all of the success we've already seen on Mars with 2 active spacecraft on the surface and that flotilla on orbit above the planet. Where are we in what we've learned? I mean, we found the water. Are we still following it? And what else have we found?
That's a really great question, in the sense that you know, there's more to it than just following the water. You know, we've seen evidence of water all over the place on Mars. That's clear. We've seen what we call reoccurring slope lineae, where water may actually be pouring down the sides of craters in a seasonal way. This is during a time period, as you can see in this slide, during indeed that summer, where the sunlight shines on the crater walls, perhaps sublimates a water plug that's sitting in, holding back water in an aquifer, and then that water pours out and runs down the slopes. we've measured that. We know it's water. Now, some of these actually may be drifts of dust and therefore producing some discoloration, but there's so much of it, and there's so many places where it's occurring. Yeah, we're pretty convinced that that indeed there is a significant amount of water locked inside the planet. Now, in addition to that, Mars seems to be emitting what we would call traces of life gases, like methane and like oxygen.
I'm knocking on wood.
Yeah, right. And indeed, although those things can be generated abiotically, for the methane, we've been observing methane from telescopes on Earth since the early 2000s. But now with Curiosity making those measurements directly over and over again, we do see that seasonal bloom for which what we call this rush of methane coming out, although it's still a trace gas, parts per billion we're talking about. And that is coming from underneath the surface. Now that could be generated abiotically. It requires water, requires certain minerals and a heat source like magma, or it could be old methane from old life in the past that is also been trapped over time and is being released. Or indeed, it could be an indication of life there today in the aquifers is what we would think. So those trace gases now are extremely important. We're making fabulous measurement of those.
And oxygen you mentioned as well. And I know that there have been, both for methane and oxygen, there have been some conflicting data, hasn't there, depending on the observer?
Yeah, indeed. The oxygen observations that we just released over the last several months is a long-term trend. It's about 5 years worth of observations, and it's a surprising trend. As the planet goes through its seasonal cycle, we expect during the winter, because it's so cold, that a lot of the atmospheric gases, in particular the trace gases, will collapse down into the surface. And then as it warms up, it actually then releases those. And what we're finding is an excess of oxygen during certain times. And then at other times, we see that the oxygen actually is being removed. So this has really caused quite a puzzle. We've had many scientists really working, trying to figure out what are the abiotic, in other words, the non-biological reasons that this is happening. And we really haven't come up with a good explanation. So the oxygen observations are really one we want to stay abreast of and see what Curiosity is going to find in the future.
Penny, have we seen evidence other than what Jim has just talked about that could indicate biological activity, or at least past biological activity up there?
Well, so far we haven't had the opportunity to closely examine materials, getting back to our previous discussion about sample return. But what we have been able to do, of course, is hook up what we understand about extreme environments on Earth and try to tease out the parts of those environments that are relevant to Mars. It's pretty clear we have nowhere on Earth that is just like Mars. It's a very, very challenging environment. But we have challenging environments on Earth that have components that really go into that Mars picture. And so microorganisms in their vast diversity, their unbelievable diversity on this planet, have adapted to a wild variety of conditions. Many of them are the conditions that we see in the Mars surface, and particularly, of course, from my point of view as someone very interested in the subsurface, both near and deep subsurface, where there is more protection from some of the nasty things that you get on the Mars surface. So I think that the importance of the gases that Jim has just been articulating is really because the atmosphere of a planet is its breath, essentially, and the breath of life on Earth is very, very clear. We have a very complicated atmospheric spectrum, which is the sum total of all of the complex gases that life on our planet puts out. When we're looking at a planet like Mars, if we're looking at life that has been not as globally, as it is here on Earth for a long time, that is something of a relict biosphere, then we would expect to see a much more subdued signal. But the fact that there is this oxygen variability and the fact that we see these traces of methane are very exciting, because what that might say about life is that if it exists in the subsurface, there's a certain leak rate, just like we have with spacesuits and spacecraft and Earth itself, and that we may be catching little whiffs of what's going on underneath. In any case, whether or not it's biology or it's non-biology, when you have a life-bearing solar system like ours, in my view, every planet matters to understanding that life, even if that life only occurs on one planet. And of course, we certainly hope it occurs on Mars or has occurred on Mars, as well as other places in the solar system.
Hear, hear. Penny, you have spent a good part of your life going to places most of us would not want to go, looking for how life has found a way to survive. One of those more milder locations, I remember being with you at Carlsbad Caverns, and you pointed to a spot on the wall and you said, "You see that? That's life eating copper." So it does sure look like the enormous variety of extremophiles that we find on our planet. It's got to give you some encouragement, right?
Oh, very much. And, you know, even though I'm a Mars fan for my entire life, of course, I have an eye on the other potential habitats. And I think that the fact that we have organisms that appear to be able to tolerate almost everything, including high radiation, and organisms that have been retrieved from, you know, space exposure and complete desiccation and living amongst metals that we find toxic, but they're busy using inorganic chemistry to make those into energy sources, makes me really understand the sweep of what our type of life, meaning organic carbon in a water matrix, is capable of. It's really quite extraordinary.
Life as we know it.
Yeah, life as we know it. And of course, you know, many of us consider life as we don't know it. And that life as we don't know it extends to other ways of making life, even out of organic carbon. So there are people thinking about other alternative sets of chemistry that might work on other planets. But from the point of view of Mars, my conviction is that we're really looking for carbon-based life in a water matrix, because Mars is not all that different from Earth. And certainly, as Jim pointed out, early in its history, it was much more similar. And so that you know, early childhood of our rocky terrestrial planets together seems to me very significant. And even Venus in its current state, which is quite inhospitable to life as we understand it, but its early history may have also, you know, shared in habitable zones. So, you know, it's not just Mars alone that is compelling, but really Mars as this beautiful red jewel within this entire spectrum, this entire crown of jewels that we have in our solar system, and what they offer for life.
Have your studies and what we've learned from others in looking for biosignatures, that key term, has it led you to the point where you think that if we had life staring us in the face, we would recognize it?
Well, yes, maybe. The slide that was just put up shows a variety, and this, of course, is from my own work. All of these colorful and drippy, gooey things that you see are all examples of microbes, as tiny as they are, but making major changes in the rock and mineral environments that they live in. So the orange stuff that you see that looks sort of like a pizza or the surface of Io, that's all rock breakdown material that's been chewed through by organisms that use manganese and iron rather than, you know, eating hamburgers for lunch. They eat rock, and they use those minerals, and then they poop out, so to speak, all of this fluffy stuff. And so they're major geological agents on Earth, but it shows that they can make their living off a geological source. You can see the screaming blue patch that one of my French colleagues is standing by, sort of in the middle lower part of the screen. And you can see an example of the same process. You were talking, Matt, about the copper material that I showed you. These are organisms all over the world that are different, but they're different and very unrelated, but they still are able to do the same thing. And so that makes me even more excited because it doesn't have to be the same organisms. It's finding a pathway of organisms in different places that can use the same energy sources. And so to me, that seems like an encouraging sign for extraterrestrial life.
Hey, if you've just joined us as we hit very close to the half-hour mark, this is the Explore Mars Life on Mars webinar, the first of a series sponsored by Explore Mars. And you just heard from Penny Boston. And I'm going to go back to Jim Green, the NASA chief scientist now. Jim, I want to jump back now to that hypothetical that I posed at the outset. That press conference, which you would very likely be a part of. I hope you're still on the job in 2024. You've got big news for us.
Right.
What's this going to mean if indeed we find evidence better than we've gotten in the past? I'm thinking of a certain meteorite, ALH 84001, that seems hard to argue with, that maybe we have found at least evidence of past life on Mars. What's that going to mean to us here on Earth?
Well, let me just mention, of course, there is an important aspect of thinking about that future when we start that announcement, and that really boils down to looking at what's happened in the past, by analogies. The ALH 84001 is a good one in the sense that, we would organize that press conference. On that press conference, we would have the scientists that are announcing the discovery, but also scientists that are a little skeptical. And so that announcement then would go out to the public, and then there would be a period where the community of scientists would really dig into the results. Perhaps if we return samples soon after that, they would then be able to have those in the laboratory, et cetera, and really tease it out, and then public reaction. And then an education has to go on to everyone in terms of the context of what this means. But if we just take that supposition that indeed in the long run it proves to be true, and we have found that second Genesis and it is on Mars, what does that mean? And here by analogy, I think we have to look at perhaps several. One comes to mind is what Copernicus did. At the time Copernicus was coming out with the theory that the planets went around the sun and not everything went around the Earth, it changed the world view. Everyone mentally had to now rearrange their thoughts about their place in the solar system and the universe. And it had a profound effect. People thought, well, we are the center of the universe because everything goes around us. And now they go around the sun just like the other planets. And then to them, that means, well, maybe there are other societies like us on other planets. This was a really profound change. I think indeed, we're going to have to come to grips with that. Many people, because of our literature and our movies, are all set to accept that there's a second Genesis out there. And in fact, many scientists, and that would include me, think it's almost inconceivable that there isn't some sort of life out not only in the solar system, but certainly on other planets. And so our worldview then once again will have to change. And I think it will change many different things. The results of finding microbes might be as revolutionary as cracking DNA. The concept of what's come out of microbiology, which is only a handful of decades old, has just been phenomenal. And that is awaiting us with this kind of discovery if we do indeed find microbial life on Mars, I think.
Penny, what would this mean to you and your colleagues, this announcement and the provision of this data?
Well, I spent my entire life doing this, and so have many of my colleagues. So I have dreamed about that happening in my lifetime. I hope it does. I'm trying to stay as healthy as possible to give it the maximum chance. And, you know, the minute we got any kind of indication that there might be extant life or even extinct life, okay, because I also do paleomicrobiology and I'm interested in the entire deep history of planets with life. The entire community would go into a frenzy of trying to test whatever features this potential life would have. And so there would be an enormous flourishing, maybe in directions that we're already pursuing, maybe in new directions. It depends on what those results would find. And then I would throw one heck of a big party.
I'd like to attend that.
Please invite me.
I will.
We should get into the topic that maybe our sponsors here at Explore Mars are most interested in. After all, they are the humans to Mars people. And that is what the possibility, evidence for not just past, but possibly existing life on Mars, stuff that's still kicking up its heels there today, would mean for sending humans there. Jim, you were a big contributor to that movie, The Martian.
Yes.
It would not be a good idea for us to head there and plant poop potatoes, would it?
No, actually, Curiosity has found the nitrogen, oxygen, carbon, phosphorus, and sulfur on Mars, all the right stuff. The soils are moist, and indeed, there's nitrates in the soils. Now, where Curiosity is sitting turns out to have alkaline soils, not acidic. So what would grow better here would be beans and asparagus. And I don't know about you, but if I had to eat 2 or 3 years worth of asparagus, I'd just take my helmet off and walk outside. But I'm assuming I could do the potatoes. I'm assuming we all are assuming there'll be more acidic soils too elsewhere. And so indeed, the analogies between Mars soils and Earth soils is really strong. And that's really quite important. If we found evidence for current life, that current life has to be below the surface. We haven't found evidence of life on the surface. And for human exploration, I think we'd have to talk about how we're going to share Mars. And I think we can share Mars. There are many approaches, unlike the Martian, where the concept was you land Ares 1, and the next time it's Ares 2, Ares 3, Ares 4. We would plan to go to one particular area, you know, perhaps 150 or 200 kilometer area called an exploration zone, where we land in one part, live in another part, and then have the ability, mobility, to go around and perform a whole variety of scientific experiments, but really confine ourselves to that part of Mars. And in so doing, then it gives us a wonderful opportunity, perhaps over several decades of continuing to go there and continuing to build and develop things at that site, an opportunity to really learn the deep, and obtain a deep understanding of what Mars is all about. And then we can take it to the next step with that kind of knowledge. So I'm all for sharing Mars. Now, you may know that many scientists, particularly Carl Sagan, thought that if we found microbes on Mars, we need to leave Mars alone and go to another body in the solar system. But I think because life also has to evolve over time, the evolution of that life is going to be completely different than ours. And that gives us, I think, an opportunity to coexist. And those are some of the new ideas that are coming out now.
Annie, what's your view about all this? I mean, I think you want to see boots on Mars as well, but
I'd like to see my boots on Mars, actually.
Me too.
But I'm going to be too old, I'm afraid. But you know, it's something I've wrestled with my entire career, because I have this desire for exploration, for our species to go beyond to other bodies in our solar system, and who knows, someday even out of our solar system in some number of hundreds of years. But at the same time, of course, I'm very aware of the deep ecology aspects of another biosphere. And this applies to Mars or any other biosphere that we may find in our solar system. And that is, how do we study it? How do we perhaps cohabit with it, as Jim points out, without doing damage to it, and in turn, without doing damage to us? I think that many years ago, probably 25, when I first started writing about the Mars subsurface as being the best place to look for life on Mars, it was not taken very seriously. We knew a lot less about the planet at that time, but we've plugged along on that theme, and I think it's become manifest that that is the place, as Jim says, where we would have the highest chance of finding subsurface life, even if Mars once was covered in life at the surface. That the subsurface, in many cases, particularly even on Earth, is a refugium, a refuge for organisms when circumstances change on the surface. We see this in microorganisms and macroorganisms. So there are caves with fish and invertebrates that have been separated for 20 million years from the surface and things of that sort. So I think that the expectation that I have is that any Mars life is going to be quite deep. And that helps us with this conundrum, because as long as we don't contaminate aquifers, as we're trying to get resources for human use, then the surface Mars environment is very harsh. And while I wouldn't call it entirely self-sterilizing, it will do a lot to reduce the plume of biological contaminants within some distance from a human colony. And then, of course, if we want to study things like the slope lineae, these trickles of water, briny water that Jim mentioned early on in our discussion, those are juicy targets, literally and figuratively. We can't wait to get our hands on them, but our hands will not be our hands. Our hands will hopefully be sterilizable robotic sampling devices that will be able to send out and bring those samples back for analysis. So there are ways to do this. And, you know, we're living through it now with this pandemic that we're all experiencing. How do we separate our activities from, in this case, a pathogen, but in the case of humans on Mars, how do we separate ourselves from potential organisms that are the Martians and keep all of us safe? And so all of these real world things are being worked out in real time. And as you know, Jim mentioned, or you mentioned that Jim is on the COSPAR panel, that dates back to the 1950s and the early part of the space age. So it's not like we just discovered that, oh, gee, there might be a problem. Many of us have served on panels and workshops, and we're writing about it all the time. So it's very, very much foremost in our minds about how to do this safely. I think we can do it. I hope I'm not being naive.
Jim, I'm really glad that Penny brought us back to that COSPAR committee that where you are the planetary protection representative from NASA, from the United States. How is this being considered by the international community? These questions of protecting Mars, but also wanting to go there and have humans explore.
Well, indeed, COSPAR over the years has looked at each and every one of the bodies in the solar system that were being considered by space agencies to go to. And indeed, early on, we didn't know much about the moon in terms of whether there would be pathogens there. And so consequently, those guidelines that came from the COSPAR committee that the international community signed up to meant that we, for a NASA perspective, wanted to implement a quarantine system. So when samples came back from Apollo 11, you know, the astronauts went into quarantine and the samples went into quarantine. And then we went through our processes of indeed interrogating those and understanding what they are, what we had, whether there were pathogens, etc., watching the astronauts over a period of time. And then finally, recognize that indeed we could have uncontained sample return from Mars. We didn't need to go through the quarantine process. And so then that means the guidelines were revised. So the committee indeed takes it very seriously that as we learn new things about each of the bodies that the space agencies are planning to go to, we take that into account to modify those guidelines. And that's been working really well. In fact, just recently, we took a good look at Phobos, and we recognized that Phobos, indeed, one of the moons of Mars, we could actually back off some of the more stringent guidelines on returning samples. And so we've categorized Phobos as a location where we can have unrestricted Earth return of those samples. And the Japanese JAXA mission is being planned to go there and has many international connections and components to it. But that required for us to bring all the knowledge we knew about Phobos forward and not consider it like Mars in a category of more restriction. And so we're going to continue to do that. And that process is working well.
We are rapidly approaching the point in this program where we're going to be turning to your questions. And I do see that lots of you are submitting them. They are being consolidated for us by the president of Explore Mars, Janet Ivey, of Janet's Planet. And by the way, I want to take the chance to acknowledge that a lot of Janet's students are watching us right now. Tapa Sweeney from India, Alex from Pennsylvania, Judah, she's not sure where he is, but Judah, welcome all of you young people, you who may actually be wearing those boots that go to Mars. We certainly hope that you'll have that opportunity and do some of this exploring for us up close and personal. Before we get to some of the questions that are coming in, I've got one more to throw at you, and Penny, you touched on it, but it's a question that Explore Mars CEO Chris Carberry posed before we started this, and that is whether what we have learned about both how we might handle isolating ourselves from life on Mars or anything else in the field of astrobiology might have helped prepare us to deal with the challenge that we're facing around this planet right now, the pandemic. I mean, do you see any relationship there?
Yes, I do. I think that one of the things that this horrible circumstance will maybe help is eventually in better public communication. You know, when you are trying to talk to people who are not microbiologists or scientists of some other sort about microbial life, it's very hard to communicate the size of these individual entities, their capabilities, and just how easily spread they are. You know, in many cases, that's very benign. There are many microorganisms that we need in our environment. They basically run a lot of the biogeochemical cycles on our own planet. So on balance, they're beneficial. We only sort of notice them on the broad scale when they're deleterious, like in the case of the COVID-19. But you can derive some lessons from this. You know, the fact that we have a new virus on the scene means even though it's related to other Earth viruses and similar to others in its group of coronaviruses, it's many different properties. And so a lot of the scrambling that's going on now in the medical and research communities is to try to figure out its properties. And so the way that we do that in real time is orders of magnitude accelerated compared to what we would have been able to do with something like this even 20 years ago. So within mere weeks, we had an entire genomic sequence for this RNA type of virus. And that was propagated around the world. And so the biggest issue is, you know, we are a world full of people with different traditions, different levels of technical sophistication, and different access to communication. And so it's the human response to that that's been the trickiest part. But one of the things that I think is important to communicate is that microorganisms, for the most part, are benign and absolutely essential to us. And so one of the things I don't want to see is an increase in sort of mindless germophobia from this. And, you know, that could be a natural outgrowth of this. But we are talking about studying microbial scale life on another planet, although we're mostly looking at bacterial size things. And if you look at a bacterium, you can probably line up maybe 80 or 100 of them across the diameter of one of your hairs. But if I were going to put viruses end to end across the diameter of your hair, I would probably put 1,000 or 2,000, right? So they're even more minuscule. So I think we're mostly focusing on bacteria size organisms. And so those are actually much easier to control and work with for the most part than the viruses, because the viruses are tinier than dust specks, whereas the bacteria are much chunkier, and so our methods of controlling bacteria and working with them in many ways are easier.
Jim, anything to add from the NASA perspective?
Well, yes. Penny did a wonderful job with explaining the various aspects of that. What's critical also to understand is, viruses aren't considered alive. They really are cellular parasites, if I were to describe them in some way, and they invade the body and they have some genetic material associated with them. But in reality, for them to live and grow, they actually have to co-evolve with a host. And so when we think about bringing material back from Mars that is alive, that life has perhaps a second genesis, perhaps is related in some way to us in terms of the fact that it started in a similar environment like Earth, but it has a completely different evolutionary track. And so the current thinking is, yes, we're going to quarantine those samples. Yes, they'll be in what we call a biolevel 4 facility, where they handle anthrax and everything else, and it will be closely monitored. But I think, as Penny points out, our ability to understand the microbial and virus environment will allow us to use those current tools to interrogate those samples and begin the process of releasing things to the science community, which will be really important to do, because that's where those laboratory equipment really comes into play. In many places around the world, that will really tease out some of the most spectacular science in terms of really having a deep understanding of that planet than we can dream of today. So those are all just right around the corner, and I'm hoping also to be around when we start cracking into that next generation.
You and me and Penny, all of us, and everybody watching this program, I am sure. All right, we are now at approaching about 10 minutes of the hour. But I have also heard from both of our guests, Jim Green and Penny Boston, that they might be able to spend a couple of extra minutes of bonus time with us. Yep. So let's go ahead and start getting to your questions. And I know that many of you are submitting them through the Zoom window, but we also got a couple. Well, I'll read one of these that was submitted ahead of time to Explore Mars. And this came from Andrew Planet, how appropriate, in Gibraltar. And so we also welcome our international audience for today's program. Andrew says, if we ever find native life on Mars, and if it had the same method of storing genetic information as we all share here on Earth, would that mean that biology originated independently at both worlds, but had evolved analogously, because it was a good solution, I guess, or that they've evolved out of a common ancestral biochemical panspermia? There's a term that we all love. Penny?
It's one of the big debates that we have, and we're not sure how to make that decision yet. If and when that arises, then we'll have to do a lot of investigation. What I think most of us are hoping for is what Jim mentioned, which is a true second genesis, where the life on Mars would be so different that we wouldn't have this conundrum. But if the life resembles ours in terms of its basic biochemistry and molecular machinery, then we're going to be faced with this conundrum. Is it uh, regional, shall we say, panspermia within the solar system? Or is it that it's such an optimum solution to make life the way that we do that it got reinvented again? And it's very hard to know how to actually go forward. And so that's where detailed work in the future would have to come to bear. I think there's no easy answer.
Jim, you're nodding.
Oh yeah, so I think the concept of, okay, we're going to look at that life, and if it is indeed RNA, DNA, has all the right stuff, we're going to want to see if there's a common ancestor. Okay,
Yeah.
and that's how that would relate to us. But as Penny points out, that's going to still be incredibly difficult, and it's really because of the fact that life has that attribute that it has to evolve, and that environment is so different than ours, on a daily basis. The temperature swing is on the surface alone is 170 degrees Fahrenheit in one day, and it's bathed in ultraviolet light, and so maybe this life has found a way to repair itself, or to survive in those environments, and that's tremendously exciting. If we can tease that out and it relates to our life, then we have new medicines, new approaches. It's just a complete revolution in our ability, perhaps, to live and grow on other planets where there are extremes. So this is just really an exciting opportunity for us that we just can't pass up. Let's find this life and bring it back.
That's thrilling. Jim, I'm going to throw this next one to you, and it comes from one of Janet's young fans, Tapa Sweeney. I apologize, Tapa Sweeney, if that's not even close to how your name is actually pronounced. She says, how can we guarantee that we are not putting life forms, our own biology, on Mars from all the probes that we are sending to crawl around on the red planet, even though we try to sterilize the stuff that goes down to the surface?
This is a really good question, because indeed it's all about that planetary protection guidelines. We early on through COSPAR and had this international agreement that Mars would be a place where potentially life could have been, or even is extant, living there today. And so consequently, those guidelines tell us that there's a level of sterilization that we want to do. We want to be able to have an opportunity not to contaminate that planet while we learn much more about what that planet is like. So we've gone through quite a program in NASA, and many of the other agencies have stated they have too, through those processes of learning how to clean a spacecraft, learning how to be able to ensure that there's a minimal or nearly as close to zero bioburden, we call it. That would be types of microbial or other types of life from Earth on the spacecraft as possible. And in particular, those places that actually touch the surface. And so that whole topic has evolved over time, for which many new and exciting techniques have come up, and we're still doing original research in that area. So we plan to keep Mars as pristine as possible in terms of not contaminating it as we possibly can. And of course, once our rovers or landers are down on the surface, they too are bathed in ultraviolet light, which really takes out another layer of bioburden that occurs by us launching it and getting it there in some sterilized form. We can't completely sterilize it, but the environment is also a sterilizing environment. So I think we're overall internationally doing real well.
And I have to apologize. That question actually came from Michael. I don't know where he is. I apologize to you, Michael, and to Tapa Sweeney. Tapa Sweeney did have a question, though, and it's more a geology question about rocks on Mars. Are they similar to what we know we have on Earth? And I think the answer is yes, right?
Yeah.
But I mean, are there geological implications for our search for life on Mars? I don't know which of you might want to answer that.
I'm willing to jump in. I have one of the slides and the backup slides, which is my number 3, I think, for Wade out there. One of the big revolutions in thinking of the last 10 or 15 years has been the degree to which life on our planet has affected. So slide 3, which would be oh, wait, let's see.
Is that your last one? Biominerals?
Yes, it's
Yes.
biominerals. I'm sorry.
Oh, it's number 7. There we go.
Sorry. We're learning to do this online thing here. So the biominerals in the solar system, it's been pointed out by a guy named Bob Hazen, who's at the Carnegie Institute in Washington, and a number of his colleagues more than 10 years ago now, that if you look at the early solar system and a lot of the bodies in our solar system, like small bodies that have not had extensive geological evolution and don't appear to have life, that you got 12 primitive minerals. And on Earth, we have in excess now, actually, probably about 4,500 known minerals on Earth today. Many of them, I must say, are found only in caves. So just giving caves a plug here.
Okay.
But, you know, in their thinking, the mineral wealth that we have here on our planet is due to abundant liquid water and the fact that we have tectonic, plate tectonics that helps to mix up the crust and down to the mantle and so forth. But the rest of that 4,400, 4,500 is due to the geochemical and biochemical interactions of life with the geology of the planet. And so one of the things that I think we're very interested in is not just the bulk chemistry of Mars, but where we find a lot of these unusual minerals on Earth are places, micro niches, sometimes hidden niches, many of them in the subsurface or at the bottom of the ocean, or in rock fractures where the life is actually working to create these minerals. And so this is another whole class of biosignatures that I think we did not really grasp in its complete form until Bob Hazen and his colleagues pointed that out. And so I think this is has been a revolutionary concept. Yeah, the slide that that Wade just put up now shows the life-produced gases, which relates to Jim's early remarks today. And then the biological molecules, there are molecules that we can see from space. Chlorophyll is the most abundant protein on our planet, and it drives the solar production of biology. But there may be other pigments that we could find. And then, of course, there's morphology. So when you add all these things up together, biominerals, real fossils, if we ever find them, microfossils, and my favorite is Baby Yoda, so I'm still holding out hope for that.
Let's see.
Well, indeed.
Go ahead, Jim.
Let me just follow up by saying, Curiosity has an experiment that actually looks at the mineralogy, and so consequently, over its 5 years of operation on the surface, it brings in material and does X-ray diffraction, and then that pattern tells us the mineralogy, the structure of how these things are put together. And right now, I think the count is well over 300 individual minerals, and of course, that we have found and discovered. And then the first thing we want to do is that a new mineral? Is that something we don't have, or do we have it? And in every case, we've said, yes, that is also exists here on Earth. But the concept then of bringing back those samples, bringing them back and actually having in the laboratory an opportunity in that rock record to look at the change in mineralogy over time, because we have cored that rock and we have that time record, is going to be incredibly important for us to understand how Mars has evolved, and evolved in a way that's different than the Earth, because of, perhaps its distance from the sun, or it's the lower mass, or It didn't have a magnetic field that kept it preserved for as long as the Earth has had. All those other factors then come in to really understand and figuring out that history of Mars. So this is really an exciting time, and that rock record is just so key to being able to tackle those questions and those things that Penny was bringing up too, all important.
Let's see if we can squeeze maybe a couple more questions in here. We
Good.
are now into bonus time, and so we thank all of you for sticking with us for over an hour here. And this one comes from, if I can find it again, from Gene of Talking Space, another great podcast for both of you, actually. Given the fact that there is an interest in Mars colonization by several commercial entities, what would the impact of microbial life on Mars or Second Genesis due to these commercial ambitions? Jim, why don't you start with that one?
Well, you know, the planetary protection guidelines that come out of COSPAR are implemented by each of the space agencies. And so our commercial entities here in the United States would indeed fall under those same guidelines. So indeed, they are just as interested as NASA is in terms of what that means relative to the exploration of Mars. So we're working together to be able to think about how we would approach colonizing Mars in the sense of that exploration zone. Commercially, we expect them to be major partners. We expect things to be landed in those areas, things that can be put together. And in fact, they may eventually have commercial astronauts that will go. But because they are US companies, they will follow the US implementation, the NASA implementation. And that's why they're interested in these topics just as well as we are. We plan to do, you know, the right thing. We think we can, but to do that, it requires these samples coming back for us to really interrogate them, learn so much more about Mars that will allow us then to revisit those guidelines and come up with a way that makes it even easier to explore Mars.
Penny, I'm going to go right to this last one and throw it to you. It's partially personal. From Rachel Tillman. What inspired you to become part of the search for life? And really a separate question, but there's some relationship. How can we integrate everybody who's interested in this, not just NASA, into sharing these findings, making them part of the public education system, like Rachel says during Apollo, where, you know, I can actually remember schools with televisions rolled into the classrooms so that we could watch the latest mission landing or return to Earth. I mean, have you thought about this, Penny? How do we share the passion that you and Jim and everybody else watching this obviously feel? Hey, Penny, you're muted there.
I think it muted me itself.
There you go.
Our computer are becoming sentient as we are all home working.
Speaking of finding
Genesis, yes.
biosignatures that we might not recognize.
So, Rachel asked what inspired me. I was a very curious little kid, like most kids are, right? And I started reading science fiction very early. That was it. I wanted to get in my rocket ship and cruise the galaxy looking for things with long tentacles and 15 blue eyes, and I still do. So I think that, you know, the arts, the science, the literature, all of that comes together and inspires us. I come from a family derived from many different countries, and that has moved around a huge amount. And so there's that taste for exploration, you know, in my background in terms of Earth. But I think the joy of what we do is impossible not to communicate. I know Jim and I and many of our colleagues go out of our way to do public events, large and small. So, you know, I have done many discussions with fourth grade classes and elder hostels and gem and mineral groups and anybody that wants me to talk, if I can fit it in, all the way to, you know, big television broadcasts that are commercially produced, or PBS or whatever. And I know Jim is the same way, and he has his own podcast, which, you know, serves that function. I show up to things, and I can't keep it inside. I mean, this isn't just a job where you kind of punch in the, you know, 8 o'clock and go home at 5 and stop thinking about it, right? This is an all-consuming lifestyle, and it has saturated my entire life. And even when I eventually go off NASA's payroll, I don't plan to go off the scene entirely, you know. And that this is true of so many of our colleagues. I think, Jim, you will have seen that too. You know, they retire, maybe they're not picking up a paycheck, they're picking up a retirement check, but they're still actively doing research, they're actively thinking and writing and talking to folks.
Yes, indeed. In fact, it's going to be the case. I can see it now when we land on the moon, where that teacher is going to say, "Class, take out your iPads," and they'll all bring up, you know, the landing where the first woman, you know, and maybe even the next woman, but at least the next man will step on the surface of the moon. Now, I was alive in high school at the time of the lunar landings, and it was just awe-inspiring, even with the grainy, yucky,
Oh yeah,
you know, black and white TV.
yeah.
And so today we're going to be doing it in high definition, and the colors will be spectacular, and the shadows will be long, and it will be incredibly eerie, but it will be just as inspirational. So everyone, you know, that hasn't seen that original lunar landing of any of the Apollo astronauts have really got a treat in store for them, and that's coming up.
What a great way for us to end this wonderful conversation. I want to thank both of you. There truly were no better people to be a part of this discussion of life on Mars and why we, examples of life down here, are so excited about it. Thank you, Jim Green, NASA Chief Scientist. Thank you, Penny Boston of NASA Ames, astrobiologist.
Thank you.
And thanks to all of you for tuning in, for joining us for this, and to Explore Mars for making it all happen, and the great people there who have been helping us out: Wade, Janet, Chris, Ron Sparkman, Adrienne. It's just been terrific, and I know that this is just the first of many that Explore Mars plans to bring you. I'm Matt Kaplan, the host and producer of Planetary Radio for the Planetary Society. I hope you'll check out our podcast, Planetary Radio, and keep looking up there at Mars, because we're there, and we're going back. Thanks again for joining us. Have a great day and stay safe.
Live long and prosper.
Live long and prosper. Thanks, Matt.
About a metric ton. We've got to go up by about 20 times for the human mission. So that's a big jump. And then things like making propellant or oxygen off of the surface or from the atmosphere of Mars, that's something else that's a big enabler. So we're looking at all this, we're gathering the data, and I think with the information we'll get out of Artemis, that'll help us from tipping that board over too far, because when we do that, we end up getting a game reset and we have to start all over again. Okay, next slide, please. Next slide, thank you. So the bottom line is, when we do all that, when we look at these things, and I think Najud made a really good point earlier, you end up with a lot of different pieces, and you have to make sure all those pieces work together effectively. So I just share this chart for everyone. This is kind of one of the ways we're looking at it at Aerojet Rocketdyne. Obviously, the SLS and Orion play key roles. The lunar experience and working at the gateway is going to be something that's important. And then we see a kind of a split crew and cargo approach, where we can ship a lot of cargo out to Mars on the slow way, like we do with ships here on Earth, but it can get there and be pre-positioned. And then we'll send the crew more effectively with something like a nuclear thermal or a chemical rocket that can get them there as rapidly as possible. So that's just a little bit of our view of the world right now. And I'll turn it over back to you, Matt.
Thank you, Joe. Boy, I suspect I was not far off the mark when I said we are looking at the biggest mission architecture challenge of all time in getting humans to Mars and back. And I'll let you folks comment on that further later if you choose. Joe, I hope you've got a bumper sticker that says Kepler rules. Can we go back, Wade, to Joe's slide number 9 for a moment? Because I love the history of space exploration and space development. And this slide, I want this for my wall.
I can make that available through the Explore Mars website if you'd like.
Would you do that? And I'm hoping, I don't want to put anybody else on the spot, but I'm sure that we have many participants out there who would love to have access to your slides as they can be made available for proprietary and other reasons. But this slide is just spectacular. I have behind me in the bookcase the Life Science Library, including Man in Space, that has the Nova rocket. Yes, man in space from early 60s, not humans in space. And there's the Nova, which, I was looking forward to after the Saturn V. Never heard of the Sea Dragon, but the other one I want to point out is on the far right, that Taurus space station, or actually it looks like a vehicle to get places. Yeah. Look at the fine print, zero gravity gymnasium. You have to take care of human needs, right?
Right.
Okay, again, thanks, Joe. We're going to go on now to the third and last of our presentations. So, Tim, take it away.
All right. Well, and before we start looking at slides, I wanted to, talk about the kind of things that we have to take into account when we're doing planning. And Joe, I really liked your triangle of competing forces, and it's always a challenge not to, push so hard that the ball falls off, right? And the other thing that I've learned as we've started to do these architectures is, there's all the technical things, there's all the trajectory things, and, Kepler rules, and there are things that you can't change. And from a technology point of view, there's always this push and pull of, well, do I wait for the big advancements in technology like nuclear thermal propulsion, or do I go now? And how do you got to be prepared for both ways and make your decisions about, okay, we're going to take this technology we have today because we know it works, but this thing is very intriguing and we want to move forward, and also to have the flexibility to incorporate new technologies as you move along. But more than just technology, there's other things that are very important. And one of those is operations. The actual execution of the mission with the ground support and the crew interacting with multiple vehicles is so important. And a lot of what we need to do at the moon to get ready for Mars has that, it comes from the operational point of view. And we've got lots of great experience with ISS and the cargo vehicles and the crew vehicles and spacewalks and repairs and science. And that is just as important as some of the technical stuff, to be able to not only do your nominal mission, but be prepared for every kind of contingency. And then there's also the political and the stakeholder aspect of mission architectures, and making sure that there's a lot of different points of view and stakeholder things that people care about. And with human spaceflight, it's never one thing about why we explore. There's exploration to explore, there's exploration to achieve great science, there's exploration to inspire the world, to take up STEM. There's all kinds of different reasons, and they're all very important. But when we think about going to Mars and how difficult that is, and Wade, if you could pull up slide 16 for me. So those historical views are awesome. I love those, and they have a different way of kind of talking about the data. This is our version from Mars Base Camp from a couple of years ago, of the recurring missions and the kind of logistics that we need to do, and the mixtures of all the different systems, cargo, crewed vehicles, and all of that. And it's important to be able to think about these types of missions. And one of the things about Mars is that, as you do your chart, the jump from 3 days to 3 years for a mission is a huge jump. And one of those things is that the crew is now on their own for the most part. And so the systems that we needed to design needs to have the reliability and the redundancy, and perhaps even the dissimilar redundancy, so that if one thing goes wrong, the crew has lots of different options to figure out what the problem is and to go fix it on their own. And that's one of the, that operational challenge mixed in with the vehicle design is one of the things that really excites me about the great work we're about to do. So let's go to chart 14. Nijun and Joe both talked about how Artemis enables Mars. But some of the other things that in that build-up to our horizon goal of being on Mars, operations, infrastructure, the science that we do at Mars and on the moon, the human experience, what is that mission going to be? All of these things we've started at ISS, and the moon is going to give us another big step up, another big ladder in working all of these different problems during a real mission, and producing the hardware for that mission. That experience is invaluable, and we can't even really predict all the things that we're going to learn, but we know that's going to be important. And another thing that I'll note is that as we keep in mind this journey that we're on, that building upon the shoulders of giants and building systems that evolve is really important. So go ahead to the next slide. And this is from a few years ago, where we were thinking about, well, from a crew perspective, the two key systems for Mars are the lander and the Mars Transit Vehicle. And the Gateway and the HLS landers are really the first step that is necessary before we get to the Mars systems. And so as we lay out a way to make these systems more capable and more and necessarily more complex to support crews for longer and longer durations, we see how we can start from where we are today to where we need to be for Mars. And we can actually probably even have overlaps here as we develop the next system. We'll test it at the moon, then we'll test it at Mars. So I'm pretty excited about the future ahead of us, and I'm really excited that we're taking those next steps with HLS. And I can't wait to be on the surface of the moon, because I know the surface of Mars is not far behind.
Wow. Thank you, Tim. I remember, and I think it was a couple of years ago, at the Humans to Mars conference from Explore Mars, was the first time I was introduced to this ambitious Lockheed Martin base camp plan. And I just wonder if you have anything that you might say about how that plan and the work that went into it, including the system architecture thinking that went into it, or mission architecture thinking, is still appearing as we move forward with Artemis. I mean, where really any kind of thinking about mission architecture, even if things go in a somewhat different direction, contributes to the goal.
Oh yeah, sure. So, the two main elements of Mars Base Camp at a high level are the main Mars Base Camp vehicle. NASA calls it the Mars Transit Vehicle, and its applicability to, starting with the Gateway, the human habitation piece, the closed life support piece. Those are still the same problems that we're dealing with. And then on the lander side, our idea for Mars is a single stage ascent and descent vehicle. And we know that will take a little bit of work, But the HLS vehicles from the announcement last week, there's a couple of different ways to do that. Or you can all, so some of them are one stage from the beginning, and some of them are starting with multi-stage and can build up to one stage. And so that really fits in well.
Yeah, three very interesting concepts announced from those three companies picked for further development of HLS, the Human Landing System. Thanks again, Tim. I was just reviewing there some of the great questions that a lot of you are submitting, which Janet is collecting for us, and we will be getting to those very, very soon. But maybe just a couple of more questions that we'll cover before we do that. And as I said, we may go a little bit beyond the 1 hour nominal length of this program today. Fortunately, all of our panelists have consented to stick around, but I'm sure we will not get to all of your questions. They will be kept, though, and reviewed, and I know that Explore Mars is hoping that all of them can be responded to as we go through the days ahead. It seems from listening to the three of you, there are still voices out there that say, why are we wasting time going to the moon? But do any of the three of you have any doubt that getting to our nearest neighbor first and proving things out is going to be a really important step in designing the system architecture that will get us to Mars and back? Nijud?
There's no doubt in my mind, right? Even as we're having the conversations and people have looked at the HLS systems and the proposals, right? A lot of people go, well, why don't you just do what Apollo did? And Apollo was awesome, and it was an incredible challenge, but they were really still very limited on where they could go on the moon because of the performance demands that come along with Kepler and the rules for getting there. And you can't even take Apollo and go and do South Pole exploration like we're trying to do. And just getting the companies and the architects and everyone to start considering how hard the South Pole challenge is, and staging something out like the Gateway for years to be able to demonstrate that operations and maintenance can be performed. Those are all precursor steps. When you say, well, let's put something in Gateway orbit, it can sit there for several years, and the Mars mission is several years long. So all of these things are actually proving those Mars systems. So there's no doubt in my mind that we need to take this incremental step, because you can't just say we're going to build everything, put the crew on it, and send it on its merry way with no test demonstration in the first place. Right? Going from theoretical to real missions involves the test and validation of your systems as you go. And really the moon is the test and validation of Mars.
Joe, Tim, anything to add?
So one thing that I'll note is that the Artemis program has that sustained operations as part of its objectives, which is very different than Apollo. And that is so important because for Mars, being so far away, having all of that, the sustained operations down, the in-orbit elements, eventual propellant production on the surface of Moon and Mars, those are very key things. And so, to your original question, there's no doubt the Moon is very important. The only thing that we need to keep in mind, though, is to always keep moving forward. All three of us on this call, our horizon goal there is Mars, and so we need to do all the testing and validation at the moon, and then it's time to move on to tackling that next challenge, that next ladder of Mars.
And I'll jump in and just add to Matt. Recently in November, we had a workshop for Explore Mars, sponsored a workshop that we've had a series of Fording Mars workshops, Achieving Mars. We call them different things as we've evolved them. But the focus of this one was actually looking at the Artemis program and looking at what is it we're going to need to know to be ready to take this jump to go to Mars. And our group that I was part of, we basically brainstormed about 85 steps in the whole process, as Nijud and Tim have referred to. We've got to get the crew out there. We've got to land, we've got to get back off the surface, and we got to come back home and get safely back down to Earth. So we took all that, broke it down into about 85 steps. Each one of those, and some of these were, technical things like propulsion. Some of them were operational things like docking vehicles. or roving on the surface, all these kinds of pieces of that overall big picture. And we found that I think it was, more than 90% of them had value from the various pieces of the Artemis program in burning down some of that risk by doing these things that we're doing at the moon. So I think that was a big validation of the idea that we can learn from going to the moon, the things we're going to need to do to go to Mars.
Fortunately, Administrator Bridenstine of NASA has said at Humans to Mars, he said it on my show and many other places, make no mistake, we're going to Mars. And in other words, the moon is not the final destination. I said I wanted to bring up systems engineering, and that's the question I posed to all three of you before this program began. There are so many factors that have to mesh in good mission architecture. But what I've learned fairly recently, in large part because of reading a great book called Spacesuit, is about the importance of systems engineering. Is it a more important factor, than the other things you have to consider? And you've talked about some of these factors, but how do you fit them all together? I mean, there's so many different areas of expertise to come up with, to design good mission architecture. Najut, let's go back to you first.
Yeah, I mean, this is really, this is my background, right? I have degrees in this, and this is my job, is making all of these pieces fit together. Systems engineering is the art of solving the complex problems with all the competing demands, and mission architecture is just the biggest, most visible piece of systems engineering, because you have to do it with multiple systems, with systems of systems. And I think Artemis is a really good example of, once you set out with a mission architecture, you set out with the best of intentions, but as you work through the design, you run into constraints and issues, and there's always this iterative process. So really, for what we have to do a lot at work is keep iterating on the design as you go. So where you started with one concept, you'll run into an issue. So, okay, well, let's tweak it and do this. And so it's that art of continuing to tweak things all along. And so you're balancing those constraints. And a lot of, like, currently the moon mission architectures, even for Artemis 1, there's a lot of balance between sunlight and, eclipsing. How long is that constraint versus what is the performance on the rocket, and how long can the systems operate, and how big is your engine burn? There are so many constraints. You're always trying to balance these things coming in. And it's really that integrator, that systems engineering job to make sure you still have a viable mission when you're done. So that is the big challenge.
I'm sorry. Joe, I saw you nodding enthusiastically there.
Oh, yeah. Oh, what Najut said was perfect. I'll throw in a little anecdote that I learned. I actually think I learned this, Tim, from somebody at Lockheed Martin when I was working on a project with you guys. But the systems engineer, their job is, you've got all these different discipline engineers, right? You've got the thermal guy, you've got the structural guy, you've got the propulsion guy, and they all see the problem very differently. And the job of the systems engineer is to take all those inputs and figure out a compromise that makes everybody equally unhappy.
Yeah, I always joke, if everyone likes you, you're not doing your job as a system.
You're not doing your job, right?
I hear the same thing from principal investigators on robotic missions. So.
Yeah.
Tim?
Yeah, and I definitely agree. Everyone equally unhappy, that's the goal. And one of the most important parts of the system engineering process is the definition of interfaces between all of the different elements. And sometimes it's, the mechanical interface between the vehicles, but sometimes it's the interface between the crew and their vehicle, and how they communicate between and control their vehicle. And sometimes it's interfaces amongst the different ground control centers. And so it could be electrical or mechanical, data or communications or fluids. And the best system engineers are the ones that can pull all of the different disciplines together and get those interfaces defined as early, as clearly, and as simply as possible. And that really goes a long way to making the whole system work well together. And often in just defining those interfaces, that you very quickly figure out, oh, this interface is going to be very complex, and we got to put some emphasis on that.
And I'd even add a little bit to Tim, because even
Please.
once you take those mechanical interfaces, you go up a level, well, you've got a rocket and a spacecraft and a lander, and now you have to negotiate between programs. So some problems mean this program has to spend money that they didn't really need to, but that might be the most efficient solution across the architecture. So it is a delicate art of balancing not just the technical, but that programmatic cost and schedule that Joe brought up earlier.
I think of the human factors involved as well. You compare this to a robotic mission where you might say, okay, the engineer says, yes, we can accelerate or we can land with this many Gs. And then the human factor person says, well, that's great. I'm glad the vehicle will survive because the astronauts inside won't. How do you integrate human factors like that into mission architecture design work?
Tim, do you want to take that one first?
Sure. So human factors or the environmental requirements for the people are just as important as any other system. And so they need to be defined and well understood. And this is a case where we've got so much data all the way back to the Mercury program that that part of it, the environmental part and the life support part, that is very well understood, and we've got disciplines all across both companies and NASA and around to do that. But also human factors often means the interfaces between the people and the vehicle, both on the ground, people putting together the vehicle or operating the vehicle, and the astronauts flying the vehicle. And there's an art and a science there to how do you display information so it's quickly understood, and how do you sort of provide the right controls to be able to quickly assimilate all that information and tell the vehicle what it should be doing. And I'm excited about the future here because now things like artificial intelligence and talking to your spaceship and those sorts of things are actually possible, not quite possible in space today, but soon. And so that's another exciting opportunity.
I'm being selfish. I would love to just keep the three of you for myself and my questions, but we are now well into the time, at least 4 minutes in, to when we are supposed to be turning to the other brilliant folks out there who have joined us, the other Martians out there, maybe I'll say, for this discussion. And it's going to be, as I said, difficult. We're not going to get to all of these, but I'm just going to pick and choose from among those that Janet has been collecting for us. Najud, this is one that is directed to you, but for any of these folks, all of you are welcome to respond. This came to us from Dustin Bergstrom. There are companies like some of yours that design and build spaceflight vehicles, labs, satellites. What about habitats on the moon and Mars? Is right now the time for bold architecture, engineering, and construction firms to begin designing those habitats? And as you probably know, there have been some really interesting competitions recently. I think we have Vera Miliani actually as one of our participants, and she leads that very innovative design competition for building habitats on Mars, some of which are way out there, at least as far as the orbit of Mars, but some of them are much more down to, I guess I should say, down to Mars. Is this part of, I guess it would have to be, right? Part of mission architecture. You got to build houses.
Absolutely. So this is absolutely the right time to be making those considerations because NASA currently has what's called the Next Step BAA broad area announcement of habitat design already in work, and Lockheed is one of the participants, and that is how do you put a habitat on the surface of the moon? How do we build that deep space 3-year Mars mission habitat for space? Those things are currently happening all over the place. And that's part of the value of we need to make progress. So even doing short demonstrations right now, looking at what do we need to put on the gateway that demonstrates a Mars habitat? What would you need to put in a moon habitat on the surface? All of those things come together. And a lot of times when you talk mission architecture, we sort of focus on the in-space stuff of leaving Earth and getting to the moon or getting to Mars. But the architecture includes what you put on the surface too. So that means, if you have a rover or a habitat, that's going to drive how long you can be there and what the crew can do. So the architecture absolutely includes those pieces on the surface, and there's lots of work going on and needs to continue going on in order to get us there right now.
Joe or Tim?
Yeah, I was just going to add that's perfect. And the other thing in our study that we did at the workshop in November, when I mentioned ISRU earlier, a lot of people think about making propellant or making oxygen. We actually looked at materials for construction as well, and that's also part of in situ resource utilization. Use the regolith that you find there to build some of these structures. One of the things that we talked about a lot, our concepts now for both the moon and Mars involve landing several times in relatively close proximity to one another. We know from our earlier experiences that we're going to blast things as the rockets come down. They sort of throw rocks, and so we're talking about building things like landing pads and things like that. So it's all part of that. Yeah, you're absolutely right. It's all part of that bigger picture that we have to start thinking about.
And the only thing I'll add is, we do have some good experience designing zero-G habitats now, and we've been flying them in the space station for 20 years. Now we get to design partial Earth gravity habitats, and that's a whole nother field where in some cases, no different from Earth, everything works fine. In some cases, that partial gravity will make a difference. So that's going to be a good challenge up ahead.
Let's go to another question. Actually, this is a question that we're getting from a lot of our younger participants out there, and it's one I was going to try and get to before we finish today, but we'll do it now. I'll use it as it was submitted by Tonya. She is a student. She wants to know, she wants to be involved in space science and exploration, but doesn't know what avenue to take. Do you have advice for students on narrowing down our interests and finding the right career path at NASA or its partner orgs? And I'm going to modify that a little bit because we're getting similar questions, like one from Estefania Osequera. She's specifically interested in how do you get into this field of mission architecture? Do any of you have advice for these two and some of our other young participants?
I'll go first. And I think that there's two questions there. And the first question is, how do I get involved in general? And NASA and industry, we need every type of person to be involved in spaceflight. We certainly need the engineers and we certainly need the scientists, but we need the communicators, we need the artists, we need the business people, we need the strategists, we need everything. And so if you have a particular passion, whatever it is, and a passion for spaceflight, there's no reason that they have to be separate. Bring what you're great at and develop that and come join our community in one way or another. And we'll welcome everything. And then to me, the specific question on the mission architecture part is, I've got lots of people on my team and Najud's team and Joe's team with different engineering backgrounds. Some of them come from the structures, some of them come from guidance, navigation, and control. And a lot of people come from the trajectory side, but it is really a multidisciplinary thing. So curiosity is important in learning about how things have been architected in the past. And then also what's very important is doing the day-to-day work on a program before you are in one of these roles, so that you know what it's like to design a mission and have the nominal mission and 16 different off-nominal missions and all the pain of doing that, such that you're prepared when it's time to think of the big picture, to understand all the little details. And then you get to take off that detailed hat and think like a fourth grader again. And if you've got the right background, then that's the perfect mix.
Joe, Najud, any advice?
Well, I'll just echo what Tim said. Everyone comes to this field from a different background. And I mean, I have the job I never knew I always wanted. Because, I just wanted to be in space and it's so cool. And like, I wanted to be a part of specifically human space flight. So I started on the space station and guidance and control and things just sort of evolved. And really my interest has always been solving those big picture problems. So first you solve them on a small scale. I did it at a system, and then sort of at a vehicle level, and now sort of at the architecting level. And that's just because my skill set is the solving the problems. And so you come in and you solve those issues, and you need the knowledge of the spacecraft, like Tim said. You need to know how it actually works and comes together, and how the operations works, and how the crew needs to interact, because you can't just step into this and go, I can design the perfect mission to Mars. You know, everyone has to come from somewhere, and it all is a big team. So you bring your niche and your capabilities, and that could be business, it could be finance, or trajectory design, and then it all comes together again. And you just have to work your way into it, because you need that depth of knowledge.
Joe, who or what do you look for when you're hiring people?
I think everything that's been said is absolutely true. And I'll just try to say, you know, one of the things that I've seen is passion is absolutely a critical element. No matter where you're coming from, no matter what your skill sets, if you have a passion for this, you'll find a place in the industry. I think the other thing for systems engineers especially, you can come from a lot of different engineering backgrounds. Some people don't even have engineering degrees. You need to have a curiosity. You need to be interested in, where does this piece I'm working on fit into the bigger picture, and what's on the other side of the wall. You know, you're not just working in your little cubicle and throwing your job over the wall when you're done. You want to know, where's it going and how does it fit together, and all those things that Najud said earlier, all those pieces that have to come together. So those are good systems engineering characteristics. And then the last thing I was just going to add was perseverance. And I'm not just trying to rip off the new rover name. The problem that you run into in this business, like in anything else in life, is you're going to hit some brick walls. And you can't stop when you hit that brick wall. You got to bounce off, you got to jump up, and you got to figure out how you're going to either get over it or get around it, or maybe you can, you know, use the brute force method and go through it. But there's a lot of times in our careers where we've run into those things, and sometimes even the whole program gets canceled, and you have to find another program. But don't give up.
I've got us now at about 4 minutes past the hour, and as I said, we're in bonus time now. We'll keep going for a few more minutes with some of your great questions. And as always happens with these, they do tend to fall, many of them, into certain categories. So here's one that kind of represents what a lot of you are asking. This specifically is from Jeff Stewart. Crewed lunar missions concepts exhibit an evolution from boots on the ground, just getting there to get back, to sustainable and reusable infrastructures. Will missions to Mars show a similar evolution, or will they be sustainable, reusable right from the start? Who wants to take that first?
I'll take that first and just keep it short, right? Yeah, absolutely. What we're trying to do on the moon is make sure it isn't flags and footprints, and then we don't go back for 50 more years, right? We need to be able to build an infrastructure that's sustainable at funding levels that can be maintained over time, and architectures and equipment that's sustainable over time. And my personal belief is that as we go to Mars, we need to do the same thing, or we'll end up with another huge gap. You know, if we send one mission to Mars and that's okay, that's all you can piece together, then we're not doing it right. And we need to have a much better evolvable architecture for the future.
Yeah, and I would say that that the absolute goal is for them to do all that testing on the moon, and then for Mars to have everything be reusable. But I also know that when you get down to solving the problems, there might be some, you know, unique thing about Mars that means, oh, for entry, descent, and landing, or something that we're almost there, but not quite. We'll do a couple of missions, but like Artemis, then, you know, we'll have that sustained, very reusable path ready to go after a few test flights.
How important has the International Space Station been to helping us learn how to maintain structures for long, long periods in space and make them places where humans can survive? Joe?
I think it's been, you know, really vital. There's a lot of, I mentioned earlier in the human side, you know, the long duration microgravity information we're getting now from things like the 1 year duration stays that we've had a couple of astronauts do now. We've certainly been able to put a lot more people up there into that environment. But then just taking another quick example, something like upgrades. We're doing the batteries now that are the new batteries for the station to replace the initial ones. The fact that we can actually go out there and take out those old batteries and replace them with new upgraded systems, that's a really critical thing for those future missions. Like Tim was saying, if we want to make these things reusable and have them be something we can use in the future for Mars for many, many missions, we need to be able to upgrade as better technologies come along. So I think there's a whole variety. That's probably just scratching the surface of things that the station's given us.
Jude or Tim? ISS?
Yeah.
Go ahead, Nujit.
So adding to that, right? So some of the big things we learned from Space Station 2 was the international partnerships, the assembly in space, the ability to actually, we can't go to Mars with just one module. It's going to take several. So that knowledge of just how you assemble in space is something that feeds forward to the Moon and the Mars architectures. And so there's so many things like that. Our partnerships, the assembly, the ability to integrate commercial now. So the fact that we have commercial cargo and commercial crew, which literally is going to launch this month, humans again, right? Those things are all like how do we do things differently? Space Station gives you that platform to test out commercial industries and stuff like that. And all of those things are already paying dividends on the Moon architectures we're looking at, and we'll do so again for Mars.
Yeah, I think that commercial and government space programs working together is an amazing lesson from ISS, such a success. I'm looking forward to seeing that plug in the Moon and Mars. And I actually pulled up some stats that I just recently been sent, so I knew about them. One of the things for these missions is the logistics and keeping everything working, keeping all the supplies, and just the sheer number of launches. So since the end of April, there's been 222 launches to the ISS, and which is a staggering number, and 41 assembly flights. And so that really proved that the things that we're talking about at the Moon and Mars, it's not those amounts of complexity or launches. And so ISS really tells me that we can go do this. We've already done it.
I like it. We can do this. As I glance through the questions, and we are nearing the end of our time here, before we throw things back to Chris Carberry, there seem to be, maybe the biggest category is still with those human factors, considering things like medical care when you're away for 2 years without an MD. Although, who knows, maybe there'll be an astronaut MD. Food, which is something we took up in the Life on Mars discussion that I had with Jim Green and Penny Boston. But let's focus on the medical services, keeping people alive and healthy. Is this something that you folks as engineers and mission architects, is this another one of those many factors that has to be integrated, how we're going to, keep people healthy enough to explore Mars? I don't know who wants to get in on this.
I'll say absolutely, right? We have a lot of requirements that come from, all that history we have. We have 50 years of human spaceflight history, more than, and all of that drives, how big is your habitat? How much is the food you need? What can you do differently with the food? So we have way more advanced food techniques today than what Apollo had, which, was a sandwich in a bag in some cases. So, we can do a lot more now. The astronauts spending a year on the space station, how do you keep them healthy? Telemedicine, all of these things are techniques that we need to get to Mars, because you need to really pack down how much stuff you have to take. So all of those challenges we continue to work on today, and there's still many challenges for this.
Yeah, and I would say another thing in our workshop that we addressed was not just the physical health issues, but also the mental health issues. So, I guess the isolation you talked about, Matt, in the previous webinar that was done by Explore Mars, but also things like, how much volume do you need for a habitat? Because people need so much space. You need a little bit of time to get away from everybody else when you're out there. Even if you're the best crew ever, that you all really like each other, it's probably going to get a little tough. And Najud said it earlier really well. We're all kind of going through that right now in our own individual houses here. But and then the other thing I was going to say is AI. We talked about artificial intelligence a little bit earlier. I think a lot of that, both telemedicine, but also because of the latency time, for the Mars missions, some of this may be dealt with an onboard computer that has a lot of medical information stored in it, so that the astronauts can call that up if an incident occurs.
Yeah, what if the doctor is an astronaut and she gets sick? You know, it's not just one doctor. Every
Right.
crew member is going to be cross-trained in everything, because they're going to need to rely on each other, and even more so than they do today.
One of the most interesting and unexpected conversations I've ever had with anyone on planetary radio was with a woman who is a dentist, who was speaking at a conference about what happens when one of your astronauts halfway to Mars gets a terrible toothache. Who's going to take care of that? And, you know, be sure to floss, everyone.
Wrong set of pliers.
Could be. We probably should wrap up here and get ready to go back to Chris, but I want to give each of you a chance to sort of sum up here. And in some cases, it's going to be repeating what you've already said, which is about, you know, are we on track to achieve this through the kinds of great systems engineering and mission architecture efforts and the development of all the technologies and other factors that are going to get us to Mars, hopefully, before another 15 or 20 years goes by. Jude, why don't you start us?
Well, I'll just sort of say, I mean, I think there's never the only other time that could have been more exciting this was 1968, when people were actually going around the moon and about to land, right? But as of today, we have real hardware, real rockets, real spacecraft, and we are really going to the moon. And I know, you know, people don't quite believe that till you see the smoke and fire and it takes off, but I couldn't be more excited about the future we have right now, because we have a real plan and we're building the real stuff that's going to get us there.
Joe, your turn.
Yeah, I'll pick up on that and say I agree with everything. And we also have characterized a lot of what we don't know, so that in this business, we put together what we call risk cubes, and then we identify what we need to do to burn those risks down. And I think we've got a lot of that information pulled together now. And, you know, I'll just say back to what we said before, I think all of us said we're going to go out there to the moon with Artemis, and that's going to be part of that process where we start burning down that risk. And I think in the next 6 or 8 years, we'll get pretty far along on that, to the point where we're much more comfortable to say we're ready to go to Mars.
Tim, take us home.
So one time I was able to be in mission control during an ISS mission, and as a shadow, looking over folks' shoulder to understand. And the fire alarm went off on the International Space Station. And it was in the middle of the night, and that control room snapped to attention, and they were ready to evacuate the space station. And I thought about, well, if you're halfway to Mars, or you're on the surface of the moon, you just can't, you know, go outside when the fire alarm goes off. And that shift in thinking that's happening right now is maybe the most important part of mission architecting, is to realize this is such a challenge and we've got the tools to go solve it. Let's think differently and let's go solve it. And so, yeah, the next couple of years is going to be an amazing couple of years where we're going to be back at the moon on our way to Mars.
Hear, hear. I hope that all of you out there have enjoyed this fascinating exploration of mission architecture as much as I have. I've learned a lot, and I feel pretty good to know that these are 3 of the people who are going to make what Ray Bradbury told us so many years ago true, that we are the Martians, or we will be the Martians. With that, Chris, I think I'm ready to turn it back over to you, and I will just thank you, Chris, and Explore Mars, for letting me host this discussion, this great conversation. And I so look forward to, first of all, watching that one with Frank White, the originator of the overview effect on the 13th, right? Wednesday of next week. Sorry about that. And then I look forward to coming back and having a conversation with John Grunsfeld, 5-time visitor to the international, sorry, I get it right, 5-time shuttle, 3 times to the Hubble Space Telescope, and that will be our topic when we talk on May 19th. Chris, get me out of here. I better stop talking.
Well, thank you, Matt. That was great. And thank you to Jude, Tim, and Joe for a spectacular session. And thank you to everybody who came on. We had a really great audience today. And so I just want to remind you about our upcoming webinars coming up. As Matt mentioned, next week on Wednesday, May 13th at 3 p.m., we have a session called The Overview Effect with Frank White, and that'll be moderated by Mary Liz Bender and Ryan Chalinsky from Cosmic Perspectives. That you can register for that now on the Explore Mars website, exploremars.org. Actually, I saw a number of registrations come in right during this webinar, so people are already registering. And on the 19th of May at, I believe we had at 1 o'clock Eastern Daylight Time, we're going to have John Grunsfeld on, 5-time shuttle astronaut. I believe he visited the Hubble Space Telescope 3 times. They call him the Hubble Hugger. And Matt will be moderating that. So more information will be posted on that very soon. Then 2 days later, on the 21st of May, I believe at 1 o'clock also, we have Star Trek actor and director Jonathan Frakes, Commander Riker from Star Trek Enterprise. He'll be joining us to talk about entertainment, space, collaboration between the space industry, space entertainment industry, and STEM education. So that'll be a great one as well. And we have a number of others being lined up over the next few weeks. So please join us. So thank you once again, everybody, for coming on, and we will post all of this information very soon. We hope to see you next week. Have a good day.
Thank you.
Take care, everyone. Thank you for joining us.
Thank you.
Space Physiology. She is the author of Stellar Medicine. If you don't have a copy, go and pick one up. It is a journey basically through the universe of women's health. And it also chronicles her adventures with the space program and her journey across all 7 continents. And she has published and delivered over 700 lectures. And in the last year, she may have become a real familiar face as she has led the COVID-19 for the American Medical Women's Association. She's appeared on Fox, MSNBC, Sky News, Forbes, and Business Insider with also helpful ideas about how to combat and to protect ourselves in this pandemic. There are so many other things that I could say about my dear friend, but I want to give you the time, Dr. Mark, to enlighten us on this idea of precision innovation in medicine for all.
Great. Thank you so much, Janet. And I want to extremely thank Explore Mars for inviting me to be part of your kickoff for 2021 and to have the opportunity to talk to you about precision innovation and why it's so important for space exploration. Explore Mars has been an amazing champion for iGiant since our inception. Chris Carberry has been at many, many of our events. Janet, we've actually had over 80 roundtables and 5 summits and 5 challenge competitions, and Explore Mars has been such an amazing partner throughout all of this. I think it's important when we talk about precision innovation, we have to first ask ourselves, why is that important? How's it come to be? I know in the age of COVID, we have begun to appreciate how social determinants of health, or in NASA parlance, human factors, or FDA lexicon, subpopulation demographics play a role. And what do I mean by that? You know, we define ourselves by age, race, sex, gender, even socioeconomic status. So we know all of that plays an important role in how we live our lives. And certainly as we take the deeper dive, we see the role of sex and gender. So what I want to do very quickly is just define sex and gender for our audience. And I use the National Academy of Science definition. Gender is really the psychosocial construct, how one sees oneself as male or female, or how they identify themselves. And sex is more the biological construct. We know the definitions are a lot more complicated. You know, we see as we interact with the environment's interacting with us and certainly influencing our genome. We call that epigenetics. And that influences how we perceive the world and how sex and gender play a role in our lives. For our talk today, let's talk about sex and gender. And I think, as we talk about precision innovation, we've talked for many years about personalized medicine and precision medicine. And we know that plays such an important role. We certainly see it with COVID, we see it with space exploration, we see it in so many aspects of our lives. Now, you mentioned that I had the honor to testify in front of the National Space Council back in August in 2019. Seems like many, many moons ago. And I introduced the concept of gendered innovation and design with this paragraph. And I just want to share it with our audience today. I said that gender and sex impact every aspect of our lives on Earth and in space. It's more than spacesuits not fitting female astronauts. We see the impact from the shoes and clothing we wear, the electronic devices we use, the cars we drive, and even the medications we take. Modifying appearances or the pink it, shrink it approach for gendered innovation will never work in any environment, including space, battlefields, hot zones, and in our homes. And who would have thought back then that the hot zones would have been in our homes? So we know that we really have to take that deeper dive to understand how sex and gender impacts our life on Earth and in space. I had the privilege also to work with NASA for over 18 years, and I've always found it an exciting place to be because as the body adapts in space, you're able to discern very small changes which have extremely important impact. And certainly we've begun to appreciate the role of sex and gender in our adaptation to space. As you mentioned, we've held 2 NASA decadal reviews to really assess how the body adapts, because we know the changes that we see on Earth from sex and gender certainly follow us into space. And then as the body adapts in space, that's just compounded. And we need to understand these changes so that we can develop the resources and the tools so that we can live and work well in any environment, including in space. So for the sake of time today, I have a PowerPoint presentation. I'm doing it as a video presentation for our virtual environment, which will explain a little bit how and why iGiant, again, that acronym for Impacted Gender and Sex on Innovation and Novel Technologies, developed. It's a nonprofit. It's an accelerator for gendered innovation and design across health, IT, transportation, and the retail sectors. And then we'll have plenty of time for questions from our audience. So let's go ahead and roll that tape. Hello, I'm Dr. Sarah Lynn Mark, founder and president of iGiant. iGiant's an acronym for the Impact of Gender and Sex on Innovation and Novel Technologies. And I want to thank the conference organizers for the invitation to join you today. I wish we could be together in person, but I hope in the near future that will happen. I will be sharing with you information about gendered innovation and how it plays a role in our daily lives, including with COVID-19. Before I start, I have nothing to disclose. I have no content to disclaim, and I am not using any off-label or investigational use in this presentation. Let me give you a brief history of iGiant. I worked as a senior scientific policy advisor in the Obama White House. During my tenure, we were experiencing an Ebola outbreak. We were also launching a precision medicine initiative. And I was also working at NASA as a senior medical advisor, and we had just published the second decadal review to look at the impact of sex and gender on how the body adapts in space. It became very clear to me that we needed to focus a great deal on gendered innovation, gendered inclusive design. So I developed the blueprint, which became iGiant. I launched iGiant after I left the White House because I did not want to politicize the issues that we were going to address. Over a period of just a few short months, many roundtables percolated across the United States, focusing on iGiant and gendered innovation. When I talk about a roundtable, I'm talking about an event which allows individuals to, one, discuss any activities that they have that has a sex gender focus. So basically sharing best practices, as well as allowing individuals to go back to their respective organizations and agencies and institutions to become ambassadors for gendered innovation. In a very short period of time, in just over a year and a half, the iGiant evolved into a 501c3, a nonprofit. And we are basically the only nonprofit accelerator for gendered innovation across health, IT, transportation, and retail sectors in the world. The mission of the iGiant is to accelerate the translation of research into gender and sex-specific design elements, such as products, programs, policies, and protocols. The vision is to improve the safety and quality of life, including work performance for men and women. I like to say for everyone in every environment on Earth and in space. Now, we often use the terms male, female, men, women, boys, girls. I really want us to take a non-binary approach when we talk about gendered innovation so that we have a more inclusive approach to these issues. Now, my next few slides talks about women's health research, and we have a very long history. I went back to 1977, and we are familiar with the thalidomide and DES tragedies and how women were barred from clinical research. For the purpose of time, I'm not going to go through this extensive timeline, and I'm sure many of you are familiar with it because you were present. Some seminal moments, such as the NIH Revitalization Act in 1990, which signed into now required in all clinical trials an analysis of results by sex for phase 3 clinical trials. And as you can see, not only was the NIH involved, but the General Accounting Office, the FDA, and there was a review back in 2000, 2001, which also showed the progress that we made and the miles that we needed to go. And in the next slide, you can see that we made significant progress, but we also knew that we needed to require sex as a biological variable to be factored into research designs, analysis, and reporting in vertebrate, animal, and human studies, including preclinical studies back in 2016. In the next slide, I think this is a report that all of you are probably very familiar with, and this was a real milestone watershed moment. It was an Institute of Medicine report exploring the biological contributions to human health. Does sex? And basically, we knew that every cell has a sex. Sex begins in the womb, and sex affects behavior and perception. Basically, it impacts health. And this was a very, very important report because it allowed many agencies to now begin to adopt new policies, including at NASA. In this next slide, if we had time, I would show you a wonderful video that was pioneered by Stanford University looking at innovation design. And I've often used this very brief video to describe to the general public how gendered innovation design impacts every single aspect of life. So instead of showing the presentation due to time today, let me just ask you some more important questions. Have you ever taken a medication that just wasn't the right dosage for you? I know for myself I have. I often tell a story of how I had taken a medication on a trip to the WHO, and it really basically sedated me for days, and it was the wrong medication dosage. Second question, have you ever worn shoes or boots that didn't quite fit? I often use that because I describe my own experiences where I'm a climber and I had to get new boots. I was given boots that was really told to me that it was designed to fit a woman's fit. Unfortunately, after I wore them, I then tore the ligaments in my midfoot when I started walking in my natural day shoe. And that really, again, was an eye-opening moment, realizing that we often market shoes and boots to fit women's feet, but we're really not looking at a woman's gait, we're not looking at the Q angle, we're not looking at how she ambulates. Another question is, have you ever experienced repetitive stress injury just by using your electronic devices? And I think this issue is so important today as all of us are wired to every device that we have around us, such as what we're even doing now. And we see repetitive stress issues. And then finally, have any of you ever sustained neck trauma in a car accident? We know that women have less musculature, muscle strength in there. We know that car seats are really designed more for the male body, and certainly the position of a human being in the cockpit or in the cabin of a vehicle will relate to how they may sustain injuries in car accidents. In fact, there was a report in 2012 published by the American Journal of Public Health that showed that women sustain 47% more severe neck injuries in car accidents. So with all that, when I designed the blueprint for the iGiant, I thought it was important to focus on these 4 sectors: health, information technology, as well as transportation and retail. And just taking it back to a moment, let's talk about COVID-19. We are seeing across the globe that men are twice as likely to die from COVID-19 compared to women across all age groups. We also see that more women on the front lines, as far as being essential workers and frontline workers, are becoming infected. In fact, 73% of the workforce that's infected are women. And we believe that it's because the PPE does not fit. as I described during Ebola, I saw women who were donning and doffing their gowns, infecting themselves. We know that gowns may not fit. We know the N95 respirator mask may have a problem with fit for women. And it's not just size and shape, it's really how the woman moves. And we need to be clear that you can't just kink it or shrink it and think that you're going to get the best fit. So the next slide focuses on health, and I want to take it now from Earth and dealing with COVID-19 to what we saw with NASA and our sex and gender decadal review. Basically, this graphic shows that every single system in the body adapts in space. And in the body, you can see in space these very dramatic changes as we adapt happen very quickly and again very dramatically. And if we had more time, I would go through every single system, but we have wonderful publications in the Journal of Women's Health which delineate how the body adapts. I do have to say that we see men and women have different reactions to radiation exposure, as well as the cephalic distribution of fluid, basically the blood that flows from the legs to the brain. And we also are seeing a syndrome, a space-associated neurosensory syndrome, where there's visual impairment and intracranial pressure. And interestingly, it's more common in men than in our female astronauts. In regard to drug toxicity, I had mentioned my trip to the WHO, and in 2013, the FDA approved new label changes in dosing for zolpidem products and a recommendation to really avoid driving the day after using this product. And it really showed that men and women metabolize drugs very differently. The pharmacokinetics and dynamics need to be filtered into any safety and efficacy study. And again, coming back to COVID-19, as we're looking at therapeutics, we need to think about that, and certainly with vaccines. We know that women have very robust immune systems. They tend to be more resistant to infection. But then once they're infected, they mount very, very robust responses. So this may account for why men may have higher mortality rates after infection. But if there is any advantage to this, potentially women may need less dosage of a vaccine to have an efficacious response. In regard to information technology, this is a really interesting area. We know that women have greater tactile sensation in their fingertips compared to men. So the devices don't seem to read when a woman's pushing down. It's almost as if she's wearing mittens on a very cold day. So what ends up happening is you have to push harder and harder over and over again, resulting in repetitive stress injury. In regard to COVID-19, we are all wired again to our devices. And then certainly with electronic medical record, we see gender bias. Dr. Burnett, who will be on the panel with me, will talk about her program, Gender Mag, which goes into further detail about how gender bias can impact how one uses even the electronic health record, and how day in, day out, that can result in increased exhaustion and burnout for female clinicians. Let's look at transportation for a moment. I mentioned to you the National Highway Safety Transportation Administration's report. And, you know, we see it with the way a seatbelt goes across the chest. We see it with the headrest. We see it even with women sustaining greater foot injuries in cars because they're not airbags in the lower part of the car, and often women are wearing soft shoes or open toe shoes. Interestingly, with COVID-19, I think a lot of us are exercising at home, for example. I know I have just recently acquired an exercise bike, and it was designed supposedly for a woman, but I know that my behind doesn't fit the seat. And we see this. We see this in transportation with the seats in cars. We see it in bicycles. And it can result in more injury and difficulty doing what you want to do. The next slide, which is stated gender branding, shows the retro barefoot caravan. And I find it quite cute. And recently, again, with COVID-19, I acquired a travel trailer so that I could get out into the outdoors and be a bit isolated, continue my social distancing. But what was interesting was this caravan that was developed in the UK and has come over to the States was using the female caravan, the female travel trailer, because it had this cute design. And it reminds me of the Volkswagen Beetle. And what ended up happening is that it became very difficult to sell these products across the gender spectrum because it was gender branded immediately. Let's go down into retail. I talked to you initially that PPE has been designed really for the average man. And imagine if you're wearing an N95 for 8, 10, 12 hours a day and it doesn't fit your face, not only does it put you at risk, but it's uncomfortable. And many women have complained of abrasions as well. So we really do need to have a better design for our PPE, for our face masks, for our boots, for our gloves. Women who were on the front of Ebola were talking about having to duct tape their gowns and their gloves, and again, putting themselves at risk for contamination when they're donning and doffing their gowns. This slide goes a little bit more into the impact of retail and the role of ergonomics. It's not just that you are alone in the environment. We have to understand how you interact with your environment. We're seeing a lot of injuries, neck, shoulder injuries now, as people are sitting at their desks and their chairs are really designed for a way a man sits and for the height of a man. So again, taking a look at every aspect of your environment will influence what you see and how you're going to be able to do your jobs. As I mentioned, iGiant roundtables were designed to empower individuals to share their best practices. And as we became a nonprofit, we have launched roundtables all across the globe. We've had also summits, which are specialty roundtables. We've had them on artificial intelligence, space, held one at NASA. We've had one for the extreme environment. We held it with first responders after the Las Vegas shooting. We had it at Nellis Air Force Base, and we had a recent design roundtable at Google. And we've had over 75 to date. What I have really enjoyed is that they're very interactive. I call them PowerPoint-free zones. And what's nice is that they can now be held virtually. We've in fact have held 5 virtual roundtables since the pandemic started. And I encourage every one of you to consider hosting a roundtable. We will provide you the tools and resources. All you need to do is invite your community. Let me just show you the iGiant structure. We have a board of directors, we have an outreach community, as well as having a corporate advisory council. But in the arms of that triangle, we also have a design advisory council, which Dr. Margaret Burnett is part of. We also have scholars and residents and youth ambassadors who are engaging our students as well. And we have a seal of approval, which Dr. Burnett helped us to pioneer, so that organizations and companies that take a sex gender look for their products can actually brand their processes as being gender inclusive designs. As you can see from this next slide, we have many different outcomes across all our design elements, across our programs, our protocols, our products, and our policies. And we just want to continue day in and day out to ensure that we see success and we see these outcomes so we can improve the lives of everyone. One future policy improvement I just have to share with you, and I know it's one that we've all complained about, is being in air conditioning, for example. And as you go in the olden days, when you would go into work sites, you would see women wearing scarves and sweaters in the middle of the summer. And part of that is because the ambient air temperature was set for men. And men, we know, tend to wear long sleeves, jackets, ties, and they also have a higher metabolic rate. And so, again, just a real pertinent question. Women freezing in their offices, how does that impact work performance? So something as simple as that, you can see can have profound impact on how well you do. I'm listing some of our iGiant activities here. One is iGiant challenges. We've launched our 5th challenge. We've had some really exciting innovation. Our first one actually was the design of spacesuits that fit men and women, a little bit ironic. The individual won an award, a prize, and that was an object flown on the space station. We also hosted one with students, over 250,000 students, and the winning design was for new hospital gowns to fit men and women. So you can see it really goes across the gamut. We have many iGiant champions. This is a partial list of some of them, and we are so grateful to everyone coming on board and really becoming iGiant champions. And I often believe with gender equity, if you build it, they will come. Some of you may recognize these scenes from some classic movies. In the beginning, we had a lot of individuals talk about gender equity, and often I would try to pivot, and then I realized it is so sentinel, so important to what we're discussing here. If you do not provide the resources, the opportunities, and the tools, careers will rot on the vine. So we believe that as employers provide these resources, opportunities, and tools, they'll be more inclined to recruit individuals, and individuals will be more inclined to stay. So finally, I just want to thank you so much, and I hope that everybody will be able to see that it is time to see the world through a gender sex lens. My contact information is on the slide, and I look forward to taking your questions. Thank you.
Again, you are so marvelous. Anytime I hear you speak, I learn something new. I think what is so exciting to me, Dr. Mark, is just that that you have brought these issues to the table. And again, it's becoming even more apparent how much we need to do this. Let's go to one of my things that I would love for you to share with everybody. Name just a few differences. You talked a little bit about the differences that happen in men
Finally, I just want
in space, but it's like one of the things that I really want, give me some examples. Don't women's blood pressure is lower, or heart rates are higher. Tell us those things that happen.
Well, thank you for that question, Janet. And that's what I was hoping would happen. We would have plenty of time to take that deeper dive again into some of these sex differences. When we launched our decadal reviews, we looked at 6 work groups that correlated with the different systems in our body. So from musculoskeletal, cardiovascular, neurosensory, reproductive, behavior, even immunological. So let's just highlight across the board very quickly a few of them from each of those different body systems. So when you look at the musculoskeletal system, we know on Earth that women are more likely, 4 times likely to have osteoporosis, basically loss of bone compared to men, and there are various reasons for it, and that can result in bone fracture. What we see in space is that as you go into space, you begin to leach calcium from your bones, and it happens actually very quickly. So within just a few weeks, you can lose significant bone. So if you think about the differences that men and women have on Earth, and then you go into space, it gets compounded. Now, what's interesting is there's a great deal of diversity on how people lose muscle and lose bone, but we have to understand the lessons here so that we can translate how to keep bone healthy, people's musculoskeletal health, healthy in space. You look at the cardiovascular system, you talked about blood pressure. That's a really interesting area. We see that women have a greater chance of developing what we call orthostatic hypotension, just sort of a nice word for when you stand up, your blood pressure drops and you feel faint. And we know that there are a lot of volume shifts in the body. I mentioned it in our presentation, that there's cephalic distribution of blood flow, everything's flowing up to the head. And we have ways to compensate. Men tend to vasoconstrict, women tend to increase their heart rates. And I think the hormonal milieu, again, estrogen, testosterone play a role in that. And that can be an issue. If you're landing on a surface that has gravity, whether it be Earth or you go to 1/6 gravity or 3/8 gravity on Mars, you need to be able to egress, get out of your vehicle and be able to do what you need to do. So we need to be really conscious of why there are those differences and what we can do to control it. We see just on Earth, for example, men and women have different symptoms in regard to heart attacks, where they may not have that crushing chest pain. It may be nausea and vomiting. So we know we have to be attuned here on Earth, and we certainly have to be attuned in space as well. In regard to behavior health, that's a really interesting area. We've selected such superstars to go into space, and I'm really excited that as we're democratizing space, basically through our commercial space sector, we're going to open it up to everybody. But we have to understand every aspect, and that includes behavioral health and mental health issues. We know on Earth, women are about a quarter more likely to be diagnosed with depression, but unfortunately only about a quarter are appropriately diagnosed and treated. And so we need to understand how men and women adapt to their environments, psychosocial issues, how they interrelate with each other, and be able to develop models so that we help everybody do very well. In regard to neurosensory, I mentioned it early on, the space-associated neurosensory syndrome. Again, there's changes in the eye structure. We see fluid shifts in the brain. Men tend to be more symptomatic. We're trying to understand the etiology of that so we can prevent this from happening or to try to mitigate it. It's interesting on Earth, we see that men and women's brains are different in the sense that corpus callosum, that little highway between each hemisphere, very, very, very busy in women, and men tend to focus using more of one hemisphere. What are some of the correlates to that? Well, we see women tend to do better after a stroke. They tend to regain the use of speech a little faster. Again, processing is different. So the neurosensory aspects, as we're seeing, for example, with COVID, with taste and smell, we see that men and women have acoustic changes differently on Earth, and that will certainly translate in space. Whereas men age, they tend to lose the ability to hear women's voices, which is interesting because they're losing that decibel range. And I often say it's a way that we can all stay together. It's an evolutionary mechanism, but it's a fascinating aspect, and we need to understand that. Immunologically, I mentioned a great deal of that in our presentation here because that is really fascinating. We're seeing long hauler syndrome. That's where people have experienced COVID, and then months and months after they've had it, they still have signs and symptoms. And we think it may be due to autoimmunity. And on Earth, women have more autoimmune diseases compared to men. So if we go into space, we know that we have suppression of the immune system. The bone marrow changes. And so we have to understand, does that put us at risk for developing cancers and relapse of infection? So we really have to take an understanding that this isn't about who's faster or better or smarter, just different, so that we can develop the tools and the resources so we give everybody the most beneficial opportunity to live and do their jobs well and safely in any environment.
You bring up the word that I think that is kind of like one of those moments where we all need to embrace it. That different isn't bad.
Right.
It isn't absurd. It isn't something audacious. It just is. And that it's like again, if you and I were to have blood drawn right now, it's like all of a sudden I might be, hypoglycemic, or my thyroid might be you might be overreacting. So anywhere in that metabolic range, just for you and I, two women, fairly the same age range, we've never had children, so we have some things in common. But again, because we are not all the same metabolically, or our endocrine systems work very differently, I just think it's very profound thing that we should all embrace this moment of different is good. It's like what makes me different adds to that thing of like, oh, we just figured out how to work on this for this astronaut. Let's do this for another, or do that kind of like more personalized, specialized thing. And you are really getting at that when you're talking about precision innovation.
Right.
And my question is, does this go to personalized medicine and personalized everything that we can think about that would make, whether it's me, like they even have said this darn MacBook Pro keyboard, everybody comments on it, that the newest keyboard is harder. You have to hit it harder. Mm-hmm. There's sometimes that I feel like I'm going to get out my hammer and like go start banging it. The darn thing won't work. Yeah. So all of these things matter because we want to be the most effective, but we sometimes tire out or get frustrated.
So let's kind of break that down a little bit. When we talk about inclusion and diversity, I often see it as being invited to the dance, but when you are actually included, when you're asked to dance, then you really have achieved your goals. And we also want to ensure that you have the tools and the resources, so you have the shoes to dance. So that's just sort of a way to think about it. For example, when we talk about spacesuits, we knew that you just can't shrink them down. You have to really look at how the body interacts with the environment. And by doing that, you're able to develop a better fitting suit. I've often been asked if, do you really need diversity? In fact, I was asked that during the National Space Council meeting, and absolutely, the answer is absolutely, in the sense that with diversity, you have improved team performance, improved work performance, improved career satisfaction. You even improve the economic calculus of an organization, of a company. So everybody benefits. It's sort of like the rising tide, all ships rise. Everyone benefits. So as we look at the new technologies that we're developing, we have so many different resources at hand to look at innovations. So for example, through artificial intelligence, 3D printing, computational modeling, we can really move in that direction of precision innovation so that we provide individuals the tools that they need to be able to live and work well and safely in any environment.
I'm going to invite a young friend of ours. She's a junior at Portland State University, and her name is Nicole Henderson. Come on in, and we're going to invite you here. I'll ask for you to ask a question in just a minute. I foresee her being one of your iGiant ambassadors very shortly. But we do have a couple of comments here in the chat. Our fantastic supporter, Jack, says that his wife is a doctor and practices practices at the Kaiser facility where you once practiced. And Elena is apparently very, very excited that that you are giving this space medicine talk. She feels like space advocacy groups do not always give enough time or attention. So Jack, always thank you for watching and being here. And Elena, we're trying to meet your requests as well. We have someone else, Janine, thank you for your talk. She's talking about being a victim of poor seatbelt design, and she's even suffered neck injuries because it was attached to the side column too high and everything like that. So how can people participate, or how can they change these things? I know you're on the forefront of this, but what do you need from all of us listening to you to enact or to request these things?
Well, I think, first of all, we have to become aware, just as what you're doing with Explore Mars and Janet's Planet, by raising these issues and having people become aware that there are differences. I think we've all too often just accepted that the way something is the way it is, and you can't change it. We know we can. So I encourage all members of your audience to participate in roundtables. Anyone can host them. iGiant will provide you the tools, will provide you the toolkit. So all you have to do is invite your friends, your neighbors, your colleagues, and we will even lead it for you. Because I think once you have awareness, I always say, once you see the world through a sex gender lens, you can never go back again. It's just, I see the universe through the prism of space using a sex gender lens. And to me, it just adds incredible granularity and clarity. And we want everyone to do that. I think the other thing that we can do is engage, especially our students, in our challenge competitions. I want people to begin thinking early on. So we host challenge competitions. So if we have organizations and companies out there and agencies, host challenge competitions with us. We have the template. We just need your audience. We need your constituents, and we'll get those messages out. I think the other way we can do it is through our seal of approval. At Google last year, we launched our iGiant seal of approval for the IT sector, and it's been absolutely fascinating to see companies look at their design processes and see what they can do. I've mentioned Dr. Burnett several times in my presentation because she was really just has been an amazing leader to help us see the world through a gender mag program that she has, so that we can see inherent bias that may be in software. And then you talked about some of the technologies. Well, that translates down. So we want to have seals of approval for every sector we're engaged in. The retail sector, I just saw that BARDA has announced a challenge competition to look at the redesign of masks, which I'm really happy to see, not just to make them comfortable, but to make them safer. We know they do not fit women's faces. So again, I recommend all of you to go to the BARDA site, put your ideas and suggestions down. And then for our students out there, become youth ambassadors, become scholars in residence. Scholars in residence are for those who graduated from college, they may be in their postgrad or their early career years, and get engaged with us. Because again, everybody who understands these issues is a potential ambassador. And I think as we do that, we move the marketplace as well. When people see that by designing and looking at precision innovation, that you get a better fit, you get a better design, the public is happy, the public wants it, it really moves the value proposition, the business proposition of a company, and they see they need to do it. So for example, with our space sector, as we look at some of the clothing, as we look at some of the tools that we need for space exploration, I really encourage our commercial space partners to take a sex gender lens look and to do it early on. When we've held summits, for example, the one that we held at NASA, the engineers said, come to us early. When we're in that formative phase, it's much easier to design early on than to try to come back and retrofit and to make it right. So let's do it early on. I think, again, for the space realm, it's really human systems integration. It's, as I mentioned early on, I called it human factors, subpopulation, demographics, social determinants. It's the intersectionality of all that we are. And we need to look at human systems integration, not only through engineering, our engineering divisions, but also clinical care. You mentioned precision medicine. And we're doing a better job of that today, especially with medications for even COVID, for example, as well as STEM and outreach and HR and research. Really every division within an agency and organization, company, we really need to ensure that there is a sex gender lens incorporated into the plan.
Nicole, as our kind of like young college student, I'm sure you have a question. What do you
I do. First, I want to say, Dr. Mark, thank you so much for sharing your perspective and your knowledge with us. It's very inspiring and very interesting to hear, everything that you know and that you've learned through your experiences. My question is, what is the biggest challenges that you believe limit furthering innovation through the gender-sex lens within the space industry specifically?
Well, I think one of the challenges is that I've often been told is it's too expensive, or that we don't have enough time, or there really isn't enough people to do the effort. And I say, no, that's really not the case. And we have seen that it doesn't also have to be used as a form of discrimination. I know people want to fit in, but we're in a world of precision now. And so we can develop the tools and we can develop the resources, which really broaden everyone's opportunities. So I think we have to change that mindset. When you look at our Apollo program, we individually handled what we needed to do with spacesuits and with training. And again, it's not to discriminate, it's just to take advantage of what each individual brings to the table so you can do the best you can. I think as I have seen that when we have had these roundtables, companies that have participated, we have a corporate advisory council, at the end of the day, they realize how important this is for their business plan because they do better. So for example, in the pharmaceutical realm, if you see that you have a medication, you appropriately dose it, then you have less side effects and you have greater efficacy. When you have tools that you're using, for example, in the construction realm, they have a better fit and people are more inclined to come and want to buy that product because it actually works for them. So we see everyone benefits and men benefit too. At one of our first roundtables, it was a transportation roundtable. And we had someone from the trucking industry, and she described that when NAFTA passed, that a lot of the men didn't want the jobs to go across the border, so they got their female partners on board, and they found that they had to redesign the trucks to make them safer, to change the cockpit, to make it easier to fix the engine, and they found everybody benefited. So I think as we take that deeper dive into the world of precision innovation, we see that everyone will benefit. We have to become aware, and we'll find that it actually is more cost effective, it is more efficient, and everybody is happier.
Now, we had a question and several questions come in. I want to go to Lindsay's question, but because I think I heard you say the word non-binary at the very beginning. But her question is this: in this research, are genders beyond male and female binary considered? What in the way that iGiant and you're looking at this as a health professional, how are you looking at that?
Yeah, so thank you so much for bringing that up. And I brought it up at the start that I really want all of us to take a non-binary approach. One of our roundtables that we had at Indiana University, we had an ambassador who was from the ACLU, and she was a trans woman, and she described that when she went into the shoe department, she wanted to buy clothing and shoes that fit her, but they weren't designed for the way she walked or for the size of her foot. So that was, nobody had really thought about it around the table. And again, that light bulb moment. We certainly see it in precision medicine. I'm an endocrinologist, so hormones are very much in my toolbox. And we have to appreciate, the full spectrum of who we are. Again, I think by raising these issues, we can hopefully diminish discrimination and expand awareness. Again, going back to that whole issue of providing those resources and tools and opportunities for everyone.
And again, just going back to realizing that everybody's a little bit different. Nicole?
Across the spectrum, gradient.
How's that next question you see there, Nicole?
Yes, I think Dr. Mark already sort of covered this, but Janine was asking, what is the cost implications for different design changes, and will businesses use the bottom line as an excuse for discrimination?
Yeah, so the economic mindset has sometimes diminished the ability for people to be creative. And what we found with the iGiant seal of approval, that as companies actually looked at a sex gender process right at the beginning, they actually found that it improved their bottom line because their products were really developed in a way that met the needs of all the community. there were individuals who were more inclined to buy them. So there might be initially a little bit of an upfront cost to raise awareness and to look at the design process, but you save at the end. Again, improving the economic calculus. It doesn't behoove anybody to have a product that doesn't fit the way your body moves or a medication for the way your body metabolizes. So it's really important to do this up front, to do it at the beginning. And if you haven't done it, don't be discouraged in the sense that you may not have been aware of it. I think people have just accepted that this is the way it's been, so this is the way it needs to be. Well, we now know that's not the case. So I'm hoping that as we raise awareness through these type of sessions, through all our various roundtables, we've had thousands and thousands of ambassadors across the globe, that we will move the bar forward so that we realize precision innovation cuts across every sector, and sex and gender is certainly one of those human factors that we need to assess early on so that we can do the best that we are able to do with the tools that we need to do those jobs.
And I think I've shared this with Dr. Mark. She happened to speak to my students, I guess it was probably last August, September. And one gal really heard you. She went into an Old Navy and was really saddened by the fact that all of the NASA shirts were in the boys sections and none were in the girls shirts. So she really heard you, and Abby wrote to the CEO of Old Navy, and I will be doggone. So shout out to Old Navy. The CEO of Old Navy sent her some NASA like shirts and everything and said, we've heard you and we're going to be moving some product into the girls area. So it's something even as simple as that we think about. And I loved your line about pink it and shrink it. I have to say, so I hope I don't offend anybody out there, my favorite color is not pink ever. So it's kind of like, it's like there's always this a little bit, it's like, why you got to make it pink? Like I like purples and blues or whatever. So there's a bit of me that nearly gets offended. Oh, this is for a woman. It's pink. And I'm like, how about I like other colors? So even silly things like that. But in your world, like, can you describe how you would, those human support systems, whether it's inside the command capsule or it's in the lander or it's in the habitat on the moon or Mars, what are your hopes for those places, Dr. Mark?
Well, as you were talking, Janet, I was thinking of the words from one of our premier fighter pilots who said she experienced emotional, physical, and spiritual harm trying to do her job, and the amount of time she wasted trying to retrofit her equipment. So I was really heartened by the military last year really looking at some of their equipment and their flight suits, for example, so that they could do redesigns so that everyone could do their jobs better. I think as we look at our habitats, we need to see what we need to be able to interact with our environments. I mean, we're all living at home now, and I certainly notice, just even in my kitchen, why are things so high up and why are shelves so difficult to maneuver? Or when I'm using some of my power tools, does it fit the grip of my hand? My own protective equipment, I certainly notice it doesn't fit me. I'm very concerned about that, for example, the N95 mask. So I think as we look at our habitats on Earth and on the moon and in our space station and certainly on the way to Mars and on Mars, we need to assume that everyone's going to react differently, and we need to test it, not just using the male model, but really looking across the board, looking at how men and women, that non-binary approach, can interact with equipment, with our clothing, with our tools. Men and women perspire differently. So our liquid cooling garments, how are they designed to meet the needs of those of individuals who are doing extreme activity? Our training protocols, women have different centers of gravity, may not necessarily be an issue as you're in the microgravity environment, the microcosm of space, but when you go to even a partial gravity environment, how does that influence? So when you're able to ambulate on a planet. So we have to look at this, and then as the body adapts, having that modular approach so that we, provide the lens for your eyesight as your body adapts with gravity, lack of gravity. You have spacesuits that are used to protect you, and men and women adapt differently. So I think we have to be aware of it. And then the other part is even communication. Men and women communicate differently. We see the world differently. And again, taking even the non-binary approach and being, cognizant of that so that we provide, behavioral health aspects so that people can communicate and interface in environments that are very challenging, and do it in a way that everyone benefits.
Nicole, do you have another question? I know that I do. If you have a question, I'll let you go, and then I'm going to have one on the heels of yours.
I do. Another question that I have, kind of relating and stemming from that, Dr. Mark, is, are there any technologies that we're still lacking that we need to really focus on developing in order to push that innovative design for space?
Well, again, I think what we have to do, what I'd like to see happen is we've had 2 decadal reviews, and I would like to go back and see the recommendations from the last review, which was conducted in 2012, published in 2014. What have we accomplished from it? What have we learned? Where do we need to go? We're looking at the Artemis program. We're looking at a shorter time frame to hopefully visit and go back to the moon and have a woman land on that surface. So I like for us to see from our decadal review, what have we accomplished? Where do we need to go? Which partners do we need to bring on board that haven't been there? And do it in a sense that it's translational, not just an academic exercise, but really look at these issues and look at it from the translational aspect. You know, we have the Translational Research Institute on Space Health, which has done a really wonderful job of putting that mindset of taking from the bench to, quote unquote, the bedside to the environment you're operating in, and how do we accelerate that process? So through iGiant, we have looked at tools to accelerate, and now we have the opportunity, working with our agencies and with our academic centers and our corporate partners and our NGOs, to really accelerate the process of looking at design elements through a sex-gender lens.
My question is, of all the lessons we've learned here in the pandemic, having our own kind of personal analogs, kind of correlating with how maybe some isolation goes on the station and in space flight, what are the lessons that you think have been the most helpful, that we can go, oh, after a long period of isolation, people begin to really kind of have some degradation of behavioral qualities, perhaps, or it's because they need to be with people, or the isolation moment has gotten to be too great? What are some things you think we've learned from the pandemic that can also help this kind of precision innovation as we go forward?
Yeah, and Jen, it's such an important question. I actually wrote an article for one of the lay press looking at lessons learned from the space program, because there are quite a few. You talked about isolation. You know, you talk about having scheduling in a day. I know men and women react differently to isolation, and I think it's important to understand that. I think, you know, we know the behavioral health aspects are critical. They're critical to the success of any mission. They're critical to the success of how we live our lives here on Earth. I think what's also interesting is the body adapts in space. So that's, you know, we have been talking about COVID and losing the sense of smell and taste. Well, in space, you may have that as well, as there's cephalic distribution of fluid, and taste and smell may be impaired. And we know eating is so important, not only for our physical well-being, but also our psychological well-being. And understanding those differences will be very, very important. And interacting in this virtual environment, I thank goodness we have it, but I know we're also frustrated by it. So what do we need to do to develop technologies that we have that tactile sensation, that haptic sensation, so that we feel more connected to each other from a, you know, humanity perspective? And I certainly think, you know, our protective equipment, I was thinking about it last night. When I went down to Antarctica, I was told I was going to be given PPE that would fit me. And when I arrived, I was given a small size boots, gloves, jacket, but it was for men. And I looked at some of the pictures last night, and I'm amazed that I was able to ambulate, to get around. I looked, first of all, like a giant penguin, with the orange boots and my black and white jacket. But I didn't have technology that really worked for me. So every time that I had to get dressed to go out, I really did not look at it with joy, because it was uncomfortable. I wasn't able to do what I needed to do. And I think that plays a role. So it really comes even down to that minutia. We need to be able to really do precise innovation to the tools we need, to the opportunities, and to train us well to do it. We each come to a task differently. And now I think we are able to define how we can interact with the environment a little better. So these are important lessons. We're all living in this giant laboratory right now, and we can translate these lessons to what we need to do to the other extreme environment, and that is space exploration.
All right, Nicole, I'm going to let you take this last question that we have gotten from Allison Robinson. Will you please moderate that question for us?
Absolutely. So Allison asked Dr. Mark, when it comes to human spaceflight systems, do you think private organizations like SpaceX or Blue Origin are better equipped for precision innovation compared to other companies like NASA?
That's a really good question. Well, first of all, I think you need a public-private partnership. You can't do anything alone. And it's the public-private partnerships that we have seen that have really accelerated the progress for COVID and certainly for space exploration. I think each one brings their own assets to the table. And it's not really, just like, again, not who's better or faster or smarter in regard to sex gender. It's the same thing with these different types of stakeholders. So it's understanding how to work together, how to complement each other. I think what they have done, the commercial space sector has done, has been truly extraordinary this year. But it's also working with the agencies to get there. So it's that hand in glove approach. And I am really excited that we are democratizing space. I hope every one of us will have an opportunity to experience microgravity, to visit the moon, to reach for the stars. And it's going to require the commercial space sector working with our agencies to do that. And I look forward to working with everyone to help achieve that goal.
All right, we've got one more question we're going to try to sneak in. Do you see AI as helping that iterative kind of design process, or helping some of those behavioral things and tactile things we need?
Do I see AI doing that? Absolutely, absolutely. And
or
I think
VR, those kinds of
yeah, VR, MR, all our tools, our technologies that we have. But again, I want to have the audience go to Gender Mag. Just look it up. Dr. Burnett's really pivotal research, because we see there's inherent bias in a lot of these technologies. They're not designed often for the way a female brain may operate, or hand-eye coordination, or even how to read facial features. So I think it's important that we understand the inherent bias in these technologies. I know Explore Mars hosted a summit about a year or two looking at this. We know that the UN has certainly done that. A lot of our partners are doing that. So we have to understand it. I mean, we see it with electronic medical record, where there's greater burnout for women because it's not designed for the way a woman processes information. Even some of our virtual reality technology, we've seen greater incidence of headaches in women. Again, that the processing of information and how the design is really not for a female brain or even female size of the head. So when we use these technologies, they are a gift, but we also have to really go back and look at some of the inherent gender bias in the initial design and processing, so that we make sure that they fit the needs of everyone who needs to use them in every and any environment.
And I cannot think of a better sentence to close our fantastic session out. We thank you, student Nicole Henderson, who I should mention is studying math and physics. So I believe you may have your thesis just right here before you. Again, we want to say thank you to everybody who joined us today. Please join us next Tuesday for Drinks with Explore Mars at 8 p.m. Most importantly, find a way to join with us as we celebrate this green run test for SLS on Saturday. Again, it will be a real historic moment that gets us ever closer to the moon and Mars. And so we are wishing all of the engineers great luck. Most of all, I want to say thank you to all of our great sponsors, all of our great attendees. Thank you for your fantastic questions. But most importantly, to my dear friend, Dr. Sarah Lynn Mark. We are all better and more informed and are thinking about things in a different way because you are here. And so we are very grateful. Everybody, we say thank you from Explore Mars. If you find ways that you want to support or volunteer or help out or have, and even want to recommend a webinar that you would like to hear, please let us know. Thank you again and have a great afternoon.
everybody. I'm Chris Carberry, CEO of Explore Mars. Welcome to our third H2M seminar, Perseverance Preparing for Launch. Before I introduce today's moderator, I have a few short announcements. First of all, if you haven't checked them out yet, Explore Mars is co-hosting Janet's Planet Online Astronaut Academy, weekdays at 10 a.m. Janet's put together an extraordinary student programming. So if you haven't checked it out yet, even if you don't have kids, I think you really should. It's really quite spectacular every day, so certainly worth tuning in. Just a reminder, the Humans to Mars Summit is now taking place on August 31st through September 1st at the National Academy of Sciences building in Washington, D.C. Registration and other details will be open again soon. And I should also note that every webinar we're acknowledging our H2M sponsors. Not all of them each time, but we're doing, trying to acknowledge all of them over the course of these webinars. Today, I'd like to acknowledge Aerojet Rocketdyne, Lockheed Martin, Northrop Grumman, ULA, Paragon, MDA, National Institute of Aerospace, and the Science and Entertainment Exchange. So thank you very much for everybody who's sponsoring the Humans to Mars Summit. Lastly, if you have any interest in sponsoring this webinar series, or even an individual webinar, please reach out to us if you have an interest. We'll post some information on this shortly, but anything people can do would be greatly appreciated to be able, so we can actually continue to do these as well. Since we're not charging admission for these webinars, any sponsorships or donations people can do would be greatly appreciated. So without further ado, I'd like to introduce you to our moderator of today's session, a longtime friend of Explore Mars, Mary Angola, the manager for space communications at Aerojet Rocketdyne. Mary, thanks for leading our panel today.
My pleasure. Thank you so much for joining us today. We have a wonderful lineup for you, and I'm very excited to welcome all of our guests. So during my day job, I get to tell stories. And so today our panel is going to tell the story of the Mars 2020 mission, and specifically the Perseverance rover. Recently, the rover was named after a Name the Rover contest that NASA had with over 28,000 entries. And so quite an enormous amount of support for this. And I think the name Perseverance is really fitting for this rover because it's going to face a lot of challenges on Mars, but it's ultimately going to make discoveries that will pave the way for human exploration to Mars. During my day job, I work a lot with NASA's Space Launch System, and that's the big exploration rocket that's going to take us to Mars one day. So the Mars 2020 rover is slated to launch this summer from Florida on ULA's Atlas V rocket. It's going to launch in a 541 configuration, which means the 5 represents the diameter of the fairing, so it's going to be a 5-meter diameter. The 4 is how many strap-ons, and so in this case it has 4 solid rocket motors built by Aerojet Rocketdyne, and the 1 is the single-engine Centaur, and so that'll use the RL-10 engine. And I want to give a shout out to the RL-10 team in West Palm Beach. They recently celebrated their 500th flight of an RL-10 last month on another Atlas V launch for the DoD's Space Force mission. So the Perseverance rover's got a really reliable upper stage engine that's going to take it to Mars, and so very excited for that. So without further ado, I want to introduce our panelists. Our first is George Tehu, and George is the program executive for Mars and lunar exploration at NASA headquarters. And second, we have Katie Stack Morgan, who is the deputy project scientist of the Mars 2020 rover for Perseverance at NASA JPL. And last, we have Neil Tice, who is the Mars 2020 Perseverance Aeroshell program manager at Lockheed Martin. So without further ado, welcome, George. And can you tell us a little bit about yourself and your role in the program?
Certainly, and thanks for having us all here. Looking forward to talking about the mission. So I'm in my role as a program executive for this mission at NASA headquarters. Largely what I'm doing is helping to keep the mission going, making sure that all the activities are moving down the field. The real hands-on work is done by the project team, which is a jet propulsion laboratory and a variety of other places with our partners, like at Lockheed Martin, where Neil is, and a variety of other places. And I've been at headquarters for about 20 years. Came in after spending some time doing some commercial space, a bit of military space, international cooperation, and then became a Martian in 2000, and have been loving it ever since. Got an opportunity to become a lunatic for a little bit and be do some lunar missions on working some instruments and on the Lunar Reconnaissance Orbiter, and then came back to Mars. So I've been working on this particular mission for a little over 8 years.
Thank you, George. And we love our Martians. So next I want to introduce Katie, who is at NASA JPL. I'm going to give a shout out to JPL. If you've never been to their website or downloaded any of their apps, I highly encourage you to do that. They have wonderful public outreach tools. So Katie, do you mind telling us a little bit about yourself and telling us what your role is?
Sure, thanks, Mary. Well, thank you to Explore Mars for having me today as a speaker. As Mary mentioned, I'm the Deputy Project Scientist for the Mars 2020 Perseverance rover. And that means I'm one of the scientists, part of a science leadership team at JPL, helping to develop and operate the Perseverance rover. And so our rover missions are usually made up of engineers and scientists, and so I'm on the science side. And so I help lead a team of over 350 scientists as we figure out what we're going to do on Mars, what science we're wanting to accomplish, and also helping the engineers design a spacecraft that can meet our science objectives. And I'm very excited for Perseverance and what it's going to accomplish on Mars, and also as the first leg of a potential Mars sample return campaign to bring samples from Mars back to Earth. And I came to Perseverance from after working on the Curiosity rover. I worked on the Curiosity rover as a graduate student at Caltech, and then moved up the freeway to JPL to continue working on that mission, and eventually got pulled over to Mars 2020 and Perseverance. And so I'm very excited to bring my experience and working on Curiosity to Perseverance as we continue to explore the surface of Mars. And so we have great things ahead of us with this mission, and I'm excited to share that all with you today.
Thank you so much, Katie. I can't wait to hear more about the science. I'm very excited for that. So our third panelist is Neil. Neil, welcome, and we're glad to have you. You want to tell us a little bit about yourself and your role on this mission? Neil, you might be muted.
All right. Thank you for the introduction. As Mary mentioned, I'm the program manager for Mars 2020 Aeroshell. I was also very heavily involved with the Mars helicopter delivery system that we'll get into a little bit later. I've been at Lockheed Martin now for almost 36 years. I actually started with Martin Marietta quite a few years before. Actually, about 3 years out of college, I had worked for Caterpillar Tractor Company for 3 years as a mechanical engineer. Caterpillar was a very good company, but I always wanted to move beyond mechanical and get into aerospace. When I graduated, I wasn't able to work for Martin Marietta at the time because they weren't hiring, but in 1984, they did manage to hire a lot of engineers, and that's when I started working for them. I've been working NASA programs for pretty much a majority of my life now at this point. Some of the first NASA missions I worked on were Magellan, TOS, MGS, GRS that flew on the Mars Observer, Chandra. I was the mechanical lead for the ACES instrument. It's the primary instrument on Chandra. Worked on Mars Pathfinder IMP camera, Odyssey, Genesis, MRO, Phoenix, Maven, InSight, many NASA missions, and 9 missions to Mars. So I'm probably one of the most experienced Mars people on the program. Currently, I'm the program manager for the Dragonfly New Frontiers mission. We just recently started that one. We're currently in phase B and getting ready for our system requirements review. So I tend to get involved very early in these programs and stay pretty much through the end of the missions. In fact, there's still missions that are flying right now that I worked on at one time, including Chandra, MRO, Maven, and Insight.
Wow, that's awesome. Thank you.
You're welcome.
All right, so let's get into the meat of this panel. So I want to first talk to George a little bit about the technology on the Mars rover. You all always at NASA put such great technology. I remember Curiosity had a laser on it, and everybody was really excited about the Curiosity laser. And so I want to know more about the Perseverance rover and the interesting technology you put on board at this time.
Yeah, there is so much going on with this mission. We have a lot packed into it. And as you noted, we're headed towards launch pad here in July. But the story of this mission and the choices we had to make on what types of technology or what types of science instruments, that story starts a good 8 years ago, shortly after the Planetary Decadal Survey came out and said that one of the top priorities was to, for the coming decade of planetary exploration, was to do a rover that would be capable of starting a Mars sample return, to be able to go to a landing site on Mars, select rocks that could potentially preserve any what we call biosignatures, records of an ancient environment that might have given a clue to life potentially being on the planet, and starting that process of bringing it back to Earth. But even further back, there was, you have to go even further back to where this capability comes from. We often talk about standing on the shoulders of giants in all our advances, and this mission is a good example of that, in that all the prior missions we've done, the robotic missions, have all been building not just in terms of the scientific knowledge that we've been gaining, but also the technology and the capabilities. And so it's really now is the right time for us to be able to do this type of mission through both what we learned from the prior missions, understanding, and actually if you could pull up, we had one image on chart number 1. This illustrates it a little bit of what all of our missions have been going towards. In our robotic program, we have 4 key goals. We want to, first among equals is trying to answer that age-old question: could life ever arisen somewhere else beyond Earth? And we're looking for that at Mars. Then just understanding the planet itself, understanding its climate and its geology. And for a long time, we've always been trying to do what we can with these robotic missions to prepare for future human exploration. And so as we progressed through that, there have been these evolving themes. The first along that line was the hunt for water. Had there been a watery past on Mars? And those early missions, particularly the Mars exploration rovers, determined, yes, indeed, Mars had a watery past in its ancient time. And then we were able to move to, well, all right, was those early environments even potentially habitable? And the Mars Science Lab, Curiosity, helped answer that question. Yes, indeed, it was able to find in the record of the rocks, a record of a habitable environment. So now we're ready to take that next step, seeking the signs of life directly onto the surface. So if you can go to the next chart, that goes through what are we doing and what types of equipment are we trying to put on this particular mission. We have 4 key objectives. First is to understand the geology of that landing site that we're planning to go to, conduct in situ astrobiology and look for those potential signs of life, put them in a cache that we can potentially go back with a future mission. And again, we're going to be continuing the experience and practice of taking measurements to prepare for human explorations, but now we're taking it the next step, something we've never done. We're actually testing technology that could potentially be useful for future human exploration on Mars. So all of that goes into deciding what type of science instruments. And I want to let Katie go into some of the details on the science instruments we picked, but they're all geared towards finding those potential biosignatures. But I will jump in here about the interesting technology demonstration we're doing to prepare for future humans, and that is an experiment that's actually going to generate oxygen on the surface of Mars. If we're ever going to send humans, we'd really rather be able to live off the land as much as we can and use as much resources at Mars as we can. And fortunately for us, Mars has an atmosphere. While it doesn't have much oxygen, it does have a lot of carbon dioxide. So if you can split that apart, you can extract some oxygen. And that's exactly what we're doing with one of our experiments called MOXIE, which is going to suck in that Martian atmosphere and split apart the carbon dioxide. And we're going to be able to actually measure the purity and the amount of oxygen that we can get out of it.
That's great, George. So I do want to come back to you later, though, to hear a little bit more about the helicopter that you're going to have. But since you've you started to talk about science, I want to give Katie a chance to jump in and talk a little bit about the science that we expect to receive from Perseverance, and how some of the science is different than the science we did have earlier with Curiosity and Spirit and Opportunity. So I'm going to let Katie jump in if you don't mind.
Yeah, so Mars is a fascinating planet and a fascinating planetary experiment. We know, based on what we know about Mars already, we think that it once had a surface environment that might not have been that different from our own planet here on Earth. At the same time, Mars also had incredible processes like impact processes and giant volcanoes. And we want to learn more about that geology with the Perseverance rover, understanding some of the major, surface processes that Mars experienced. Impacts, volcanics, history of water on the surface, and we can do that with Perseverance. But of course, the real key and kind of key of this mission is the search for ancient life. And George mentioned biosignatures, which are basically any kind of pattern or texture preserved in the rocks that indicates that life might have once been there. And with the Perseverance rover, we have a very unique payload, different from previous missions, that makes us uniquely well suited to searching for signs of biosignatures in a way that previous rovers have not been able to. So if you pull up slide 5, which is an image of the rover and its payload, I just wanted to point to some of the features and instrument payloads that make this rover so unique. So if we can get slide 5 up. What I want to highlight as we're waiting for that are the instruments on the arm of the rover. So the rover has instruments. It has instruments in the body of the rover, as well as the mast, which is the head of the rover. But what really distinguishes this rover from previous rovers are the instruments that we carry on the rover's arm, which are out there on the end there, nearly touching a rock. And the instruments I want to mention are the Pixel instrument, which is an X-ray spectrometer to look at the chemical composition of the rocks and soils, as well as the Sherlock instrument, which can look at organics and the composition and mineralogy of the rocks. And what's different about Perseverance compared to rovers like Curiosity is that Perseverance can actually map very fine scale textures with very fine scale composition and organics. And that kind of mapping in combination of textures and composition is exactly the way that we search for biosignatures in ancient rocks here on Earth. And for the very first time, we can do that on Mars in a non-destructive way. Previous rover missions have ground into the surface, collected powders, and looked for things like organics. But in doing so, they've destroyed some of those fine scale textures that are essential for making the case for a biosignature. And so with Perseverance, we have an instrument payload that it uniquely suits us to looking for signs of ancient life on Mars and making the best decisions about the samples that we're going to collect and hopefully bring back to Earth to really answer that question: did life once exist on the surface of Mars? And so we're really excited about that. And so of course, the search for life is a main objective for us, but we also hope to learn more about the evolution of Mars as a planet and the processes that turned Mars from a planet that may once have been habitable into the kind of cold, barren desert it is today, and understand the story of a planet as it evolves. And we can do that in situ on the surface with Perseverance, and also with those samples that we hope to bring back.
Oh, that's amazing, Katie. I can't wait for this rover to make it there. So George, I'm going to go back to you because I want to hear about the helicopter. I'm excited about the helicopter as a technology demonstration. So can you tell us about what it's going to do and what its purpose is?
Yeah, absolutely. Interesting history. When we put out the call for what types of science instruments we want to have on this, it was very broad and technology investigations. There was actually an idea to do some sort of helicopter that was proposed. Turns out wasn't quite ready yet, but it was worthwhile doing some technology investment in it. And so a few years went along, and JPL, who had proposed it, actually did make quite a few advances, and they got to the point where, yes, it was definitely viable. So we made the choice that this is a good example of a very high risk but high reward opportunity to have a secondary payload. You don't get a chance to go to Mars very often. And while the rover itself and our objectives for seeking signs of life and doing our other objectives are the prime mission, it created an opportunity that the helicopter could ride along and do its own demonstration of, is it possible to actually start having a new dimension of mobility at Mars, now in the aerial dimension. So fundamentally, it's going to, the size of it is, I can hold my hands up, the body of it is a little bit, almost CubeSat size, one cube, a little bit bigger. But it's solar powered, has 2 counter-rotating rotors that about a little over a meter in diameter. And what we do is we carry this on the bottom of the rover. After we've landed, we'll be able to deploy it, and it'll, in the first earlier parts of the mission, that's really our opportunity to do a few test flights. So it's a fairly short duration demonstration opportunity. Couple of test flights, taking it slow first, small hops, then trying to go push some of the capabilities beyond that. And really looking forward to seeing how it operates actually in the Martian environment. We've been able to effectively fly it in simulated environments here on Earth in vacuum chambers, but now seeing how it really works on the surface of Mars, trying to communicate to it. We have to communicate through the rover. It's our relay to speak to the helicopter, and it'll do a couple of demonstration flights and potentially pave the way for future missions that might use a similar technology.
Wow, that's great. I'm very excited about this. So George, your team helped work on the deployment mechanism for the helicopter. So can you talk a little bit about what that is and what that entails? Not George, I'm sorry, Neil.
Sure. If you could go to slide, let's see, 15. So before I get into it, about 2 years ago, JPL came to Lockheed Martin asking if we could work on this Mars helicopter delivery system. They had a concept of putting the helicopter on the belly pan of the rover. And so we took that concept that was basically just a bunch of drawings that somebody had come together to install it onto the belly pan and matured that design to the point where we could start building hardware. What you can see on the bottom of this picture is you can see the belly pan of the rover, and you can see a large black object, which is the debris shield that protects the MHDS or the helicopter during landing. So I think you'd like to know a little bit more about how this operation will work. Well, the first operation, once the rover is on the surface and spent about 30 days checking out all the various subsystems, they'll be ready to drop the helicopter. So the first procedure in getting that helicopter onto the ground is to drop the debris shield. If you could go to chart 25. Okay, you can see the front view of the the rover like you saw previously. You can see the debris shield in the top picture. There's a cable cutter that will be fired to release that belly pan or the debris shield so that it drops down to the surface. The rover is now able to drive away from the debris shield to get it out of the way. And then that starts the process of releasing the helicopter from the belly pan. There's some launch locks that fire initially to kind of release the helicopter. There's another release mechanism that will be fired to allow the egress arm to rotate downward. In the picture C, you can see how now the helicopter is at least vertical. There's another set of mechanisms that have to be fired to release the legs. So you can see the first two legs have popped down and then the second two legs. And then the final release is another frangibolt, which is fired that allows the helicopter to drop down to the surface. The helicopter has very springy legs that allow it to just kind of bounce, and it just need enough clearance that the rover can drive away and leave the helicopter sitting on the ground.
Oh, that's awesome. I'm looking forward to that, Neil. So I want to move a little bit more to launch now and talk with Katie, if you don't mind. How's the science team preparing for launch? Especially, how are you able to accomplish all the tasks you have to do with so many of you probably working from home right now?
Yeah, fortunately, Mars rover scientists are very used to working from home or from different parts of the world. For curiosity and opportunity and spirit, our science teams are spread all over the world, and we call in every day to work together to operate rovers. So in a lot of ways, we've been preparing for this type of situation for a while. And so, we're continuing to work from our own, dispersed locations. But our science team right now, we're gearing up for launch and getting excited for landing. And what that means for us on the science side is really digging into the data that we have about our landing site and learning as much as we can about the geology of our landing site and doing as much preparation and planning as we can before we get there. Because the minute we land on the surface, we're going to have a lot of decisions to make. Where are we? What rocks do we think we're looking at? Where do we think we're going to drive? What's our first stop going to be? What's our first sample going to be? And so we kick off this whole series of decisions. And so the more prepared we can be to make those decisions, the better off we'll be when we're on the surface, when we're also experiencing the, being on Mars for the first time with this rover and checking out the instruments. And so the more prepared we can be, the better. And so what our science team is working on, we recently finished the construction of a geologic map of our landing site. And so mapping is something that geologists do here on Earth to understand the geologic history of rocks here. And so we did that for our landing site, but using orbital data, so images taken from orbiters around Mars. So we created this geologic map, and now what we're doing is we're digging into that map to identify the very specific locations and questions that we want to ask with the Perseverance rover, and trying to find those spots where we think we can answer those questions, which units we're going to look at, which minerals we're interested in studying, and where do we think the best exposures of those locations are. So we're working right now with the science team to come up with a science mission plan for what we're going to do on the surface, and identifying the questions, the locations, and the potential samples, and even coming up with representative rover traverses to anticipate what we're going to do when we land on the surface. So of course, when we get to Mars, we're exploration driven and discovery driven, and Mars always throws a few curveballs at us. But the more we can do right now to prepare and be ready, I think the better we'll be at operating efficiently on the surface and accomplishing our science objectives. So that's what the science team is working on now. And actually we had a telecon going just before this webinar that I was dialed into, and we were talking about, objectives for atmospheric science. So we meet every couple of weeks and we have conversations like that with the science team. So we're going full steam ahead on those preparations, and we're excited for landing and launch.
That's awesome. I had forgotten that you're used to working remotely. So that's really good that this isn't slowing you down.
Yeah.
So George, can you tell us sort of what are the next major milestones before launch?
Sure. Actually, if you can pull up chart number 3, gives a timeline of kind of where we've been and where we're going in terms of the progress of the mission. we've been designing, building, testing the rover for the past couple of years. And now pretty much all the hardware is down at Kennedy Space Center being prepared for launch. We've actually already got the rover is finished its functional checkouts and is had its various deployed components stowed, getting ready to be stacked together with the other components of the mission to prepare and putting it in the configuration that we call the cruise configuration. That's the image you see there where it says cruise to Mars, where we have the rover packed inside the aeroshell, and then what we call the cruise stage attached with the aeroshell that helps get it to Mars. So actually, if you can go to the chart number 6, this shows some of that testing that has been going on. Now, this is not at Kennedy. This is prior to that. This is our first driving test of the rover, and then also putting all the components together and putting it through a space simulator, simulating the cruise to Mars. So as much as we can do to simulate the journey to Mars, we're trying to do on Earth. Can't quite do everything, but we can come as close as you can to it. If you go to the next image, this is where we are today. And this is our rover at Kennedy Space Center getting its weight checked. We call this a mass balance. We put it on a rotating platform and make sure that we fully understand where the center of gravity is, have to put on some ballast mass in certain places. And that's now complete. So you can see the rover is all tucked up. And I will point out here, you can see our nameplate right there, Perseverance, looking mighty nice on the robotic arm. So the team there at Kennedy is preparing the spacecraft to get it in that cruise configuration. Over the next couple months, once we get it all put together, then it will be integrated and encapsulated with the launch fairing that United Launch Alliance provides our launch vehicle, the Atlas V that you described earlier. It'll be put into that launch fairing, and then that whole component will be transported to the Cape Canaveral Air Force Station side of the launch area. We're going to Launch Complex 41, which is where we'll launch out of. Take that whole component to what they call the vertical integration facility, right next to the launch pad. Then that whole, the fairing with the spacecraft inside it will be hoisted up, put on top of the Atlas Centaur rocket, and then we await our launch date for rollout and launch. Our launch period opens on July 17th, and we're getting ready for that. Now, I want to throw in, point something else out. Katie mentioned how her team, at least the science team, is used to working remotely. A lot of our Atlo team, of course, is not. And when you're doing the hands-on work, that can't be done. I think a lot of people are asking the question, how is the team handling this new environment where a lot of us are needing to be remote? And roughly a majority of the team is now doing teleworking. There are the small numbers of teams that are who are the mission critical, finishing up a couple of pieces of sampling hardware at Jet Propulsion Lab, but the majority, a lot of that effort happening there at Kennedy. And I do want to point out across the agency, the first priority has been to the health and safety of our workforce and also the communities that we're around. So we've been very successful so far in making sure that both our team and the communities they're in are operating in a very safe manner.
Thank you, George. I'm glad you all are staying safe. Before we move to landing, because I'm seeing a lot of questions coming in asking about the landing and operations. But Neil, I just wanted to check in with you if you had any fun facts you wanted to share about the launch.
Oh, it looks like somebody already unmuted me, so I don't have to. So yeah, I've got one fun fact that is kind of fun to talk about. The ride on the Atlas 541 is a pretty rough ride, and the payload gets exposed to up to 6.5 Gs of axial acceleration during the launch. and up to 5.5 Gs of acceleration laterally. So it's a pretty rough ride, but believe it or not, that's not the roughest ride it's going to see. The real rough ride occurs during entry, descent, and landing, whereas the aeroshell hits the atmosphere, there's a deceleration of up to 12 Gs, which puts an extreme load on the front of that heat shield as you're slowing down. And that's really the design requirement for the aeroshell, was that 12 G load. So that's kind of a fun fact that normally launch is the worst environment, and in this case, EDL is the worst environment. Another fun fact is during launch, it's very noisy if you're to be right next to that launch vehicle. And a comparison of how loud that noise level is would be if you were standing right next to a jet engine on takeoff. That's how much noise is generated by the rocket engines on the Atlas V. And so it's a pretty noisy atmosphere that creates all kinds of vibrations inside the fairing where the payload is sitting, and can see up to 18 Gs of vibration just from that acoustic level on the launch pad. And then I guess the last fun fact is the Atlas V really has to get going fast in order to escape the pull of gravity from the Earth. And in order to get headed on its way to Mars, it has to achieve at least 25,000 miles per hour of velocity before it gets away from the Earth and on its way to Mars.
Thanks, Neil. I'm glad we had those facts. We're ready come July 17th to share those tidbits with our friends. Yeah. So Katie, let's talk about landing, because I think that's what folks want to know about. And so we'll get into the technology, but let's talk about sort of the science in picking a landing site. So you mentioned earlier there are orbiters around Mars. So we've had 8 successful US landings with landers and rovers, but then we also have these orbiters, and probably one of my favorite is the Mars Reconnaissance Orbiter, which has the HiRISE camera, and it took a gorgeous image of Victoria Crater back in 2016, and I think everybody knows that image. It's kind of an iconic image of Mars, at least in my mind, and that really helped the science team look at the terrain that Opportunity was going to have to traverse. And so you spoke to these orbiters and how they play a role. Can you talk about the landing site for Perseverance? What is it called? That was one of the questions that's come into us, as well as some of your decision making that went into picking that landing site and some of the challenges with it as well.
Yeah, absolutely. And so if we can bring up slide 17, I think I'll start there. But our landing site is Jezero Crater, and you can see that here. And I'll mention that the selection of our landing site was the culmination of a 5-year process involving the community, the Mars community, and any other interested folks in the community who wanted to weigh in and provide perspective on where the right place was to send the Perseverance rover. And so the result of that 5-year process was the selection by NASA headquarters of Jezero Crater as the place to go with Perseverance. And so what this image shows, this is topography of Mars, shows the location of Jezero relative to some of the other big geological features in the area. So Jezero Crater is on the inside rim of one of the largest, oldest impact basins on Mars, and that's the Isidis Impact Basin. And we think that the Isidis Impact Basin formed about 3.9 billion years ago. So these are old rocks here. And this is one of the major impacts that we think happened on Mars. But not too far away from Jezero and Isidis is Syrtis Major, which is one of the major volcanic centers on Mars. And so Jezero Crater has this unique position, being very close to major impact related terrain on Mars, but also close to a major volcanic center. And if we go to the next slide, what is particularly special about Jezero, in addition to this general setting, is the presence of a delta within the crater. And we think that Jezero Crater was once the site of an ancient lake basin. And there are a number of places on Mars that we think might once have hosted ancient lakes. But what's really special about Jezero Crater is that it's a slam dunk. We have not only the delta that we see, and we recognize landforms like the Jezero Delta here on Earth and deltas that we have here, but in this crater, we have an inlet valley, which tells us that water flowed into the crater. But what is unique about Jezero is that it also has an outlet valley, and we don't always see that in craters on Mars. So we know that this crater once filled up basically like a bathtub to the point where it overflowed out the outlet valley. And so that's really important for us as we're thinking about what a good landing site might be, because not only do we have evidence in the rocks in the delta that a lake was there, but we know that there was enough water there for a significant amount of time to basically fill this crater and then overflow it. And sometimes we think in different places on Mars that water might have been a kind of figurative flash in the pan. But here in Jezero, we know that that water was around long enough to fill the basin. And we think that might have been a great place for life to exist and take hold. And we have the types of rocks, similar to rocks here on Earth, that are very good at preserving that evidence of life. And deltas here on Earth are great places to go to look for organics. And we hope that the same is true here in the Jezero Delta. If you advance to the next slide, I'll just point out that the other thing that's really unique about this location, and this, what you're seeing here is a false color image from one of our orbiter spectrometers. So this is an instrument that tells us about mineralogy. And the colors highlight the fact that there's a lot of mineralogical or compositional diversity here in Jezero Crater. And what you see here in green, those rocks there on the inner margin of the crater, those rocks contain carbonate. And when you think about carbonate, you might think of reefs in the Bahamas or in Australia. And honestly, that's kind of what we think about too. We don't know that that's what we have here, but we have carbonate rocks in what was perhaps a shallow lake environment. And that's a great place for both hosting life and preserving life. And so we're really excited about Jezero Crater for a number of reasons. We know it had water for a significant amount of time. It has the rocks that are really good at preserving evidence for life. And we have a number of very interesting and unique geological and astrobiological targets here in this location. And another special thing about deltas is that they're really good at concentrating and collecting rocks from a large area into one place. And so that delta right there represents, sediment grains in that delta came from very, very far away outside the crater. So by going to this one location in the crater, we can sample locations far, far away that we might otherwise never have been able to go with the rover. So deltas are really good at concentrating a geological story in one place. And so these are some of the reasons why we've been so excited about Jezero Crater and the potential for exploring this with the Perseverance rover and helping us understand the surface of Mars and Mars's potential for hosting ancient life.
Wow, this is great. So I think a lot of us know landing on Mars is really difficult. And so, Neil, I want to ask you about why is it so difficult to land on Mars? And then can you tell us about the aeroshell and the heat shield and how that's used to protect the rover during the landing?
You could go to chart 10 for me. Thank you. Okay, so entry, descent, and landing is a very complex process. There's lots of things that have to go right in order to get down to the surface. And that's one of the things that makes it so difficult. And there's been a lot of failures at Mars. Fortunately, JPL's been very lucky at getting most of their spacecraft to Mars, but some of the other countries that have tried have not been quite so lucky. Just to give you an idea of the complexity, the spacecraft essentially takes 6 to 8 months to get to Mars before it's ready for the entry phase of the mission. And the first thing that you have to do is separate the crew stage from the aeroshell. And so now the aeroshell is floating on its own, heading towards the atmosphere. It does have thrusters to adjust the angle of the spacecraft of the aeroshell as it hits the atmosphere. Since it was previously installed on the cruise stage, they we do have to adjust the center of gravity of the aeroshell before it hits the atmosphere. And we do that by deploying a bunch of very heavy tungsten masses. They're actually 2 tungsten masses, weigh about 164 pounds each. And that sets the gravity where it needs to be as it hits the atmosphere. The spacecraft is really on its own at this point. Everything is robotically controlled and pre-programmed, which means you have to do it right the first time. There's no joysticking this spacecraft as it comes in. So as you hit the atmosphere, the aeroshell is the primary protection for the rover that's inside it. There's a peak heating phase where the heat shield gets to about 3,500 degrees surface temperature on the outer surface. And that aeroshell protects the rover from seeing those high temperatures. There's a thermal protection system called PICA that protects the rover by ablation. It allows the heat to flow away from the spacecraft, and the back shell also does some protection there. But once you get through that peak heating, now you're just kind of coasting. There's some additional balance masses that are released. 65-pound masses are ejected from the aeroshell. And that allows us to kind of surf our way through the atmosphere to the final landing point. And so it's actually, very ingenious. There's lots of things going on during EDL. All of these have to happen just right. The next major event would be to deploy the parachute. Parachutes, seen a lot of testing. We're very confident in this parachute. JPL did all the testing, but there's always things that can go wrong with parachutes. And then after you've coasted on the parachute for a little while, then the heat shield is released from the rest of the structure. And there's some very good videos on YouTube showing the MSL heat shield leaving the back shell. And that allows the radar to turn on at the right time to see how far above the ground you are and determine the final landing points. There's lots of cameras on board that are used to optically navigate the spacecraft to a safe landing zone. The Sky Crane was developed by JPL to allow various separation hardware to fire and lower the rover down to the surface so that it can fly away. So all of this has to happen in 7 minutes. So anytime one of these happens, it's just very exciting. There's lots happening and lots that has to go right. So as soon as you hear that, the word that you've touched down safely, there's a lot of cheering that goes on.
Oh, that's wonderful. 7 minutes of terror. I can only imagine.
I had some questions about the back heat shield.
Yeah.
I do have a picture on slide 11 showing you the heat shield. So this is the picture of the heat shield with the TPS ablator installed. We use a material called phenolic impregnated carbon ablator. It's actually a carbon weave that gets impregnated with phenolic. Phenolic is what ablates off that surface and allows the surface to stay cool enough that it doesn't soak back into the rest of the spacecraft. The next slide, you can see the overall aeroshell. Slide 12, please. So here's some additional hardware that's on board this aeroshell, in addition to, and most of it is mechanisms. I talked about the balance mass devices that are ejected. That was all part of the aeroshell mechanism. There's also 9 separation fittings that are fired in sequences of 3. That is all hardware that was built at Lockheed Martin and had to be tested. There's a Medley 2, which stands for Mars EDL Instrumentation 2. MSL also had that hardware, and it measures things like temperature of the surface, the amount of ablation that's occurring, the pressure on that front surface of the heat shield. All of that hardware is installed and will be active during the EDL event, so we get information for future missions. The back shell also has a ablator product on it. It's called SLA 561B. It's the same material that was flown back on the Viking program. So a lot of this, this technology has been used in the past. The structure itself is almost totally M55J composite materials. It has to be very, very stiff to withstand the high pressure of entry. There's 2.5 inch thick honeycomb on the heat shield structure that adds to that stiffness. So it's a seems very simple, but it's a very complex piece of hardware. So.
That it is, and it's got to withstand those extreme environments. So thank you so much for building that. So I'm seeing some questions about if there's aero braking and a little bit more on the entry, descent, and landing. And so, George, can you talk a little bit about the sky crane that Neil mentioned, and why is that the suited landing mechanism versus other landing systems?
If you're familiar with how the Curiosity rover landed, then to the untrained, well, it looks very similar, right? But there's actually a lot extra going on for Mars 2020 and Perseverance that you can't actually see. A lot of improvements. And part of that starts with the sky crane and the descent stage. And there's two key new capabilities that we're going to have for Mars 2020 that Curiosity didn't have. One is called range trigger, and the other is terrain relative navigation. Range trigger is all about when do you pop the parachute. Previous missions would be able to, as they're coming in to landing, they've got an estimated velocity and estimated distance of the surface, and they determined on when to pop the parachute based on their velocity, a certain velocity marker. We were able, by just changing one line of code in the system and using other measurements in terms of our range to the target, we're able to now to pop our parachute based on our actual estimated range to where we're going. What that helped us do was shrink the size of what we call the error ellipse, or the landing ellipse. So where Curiosity was shooting for a target, ellipse that was 20 by 25 kilometers, we've been able to shrink ours down to about 8 kilometers diameter circle. So that was really what enabled that, and then terrain relative navigation enabled us to choose Jezero Crater because it helps us get to more interesting landing sites that the scientists want to get to. Terrain relative navigation is very similar to how some of that is done here on Earth in different systems, but we have a downlook camera that's on the bottom of the rover, and as we're coming down with the descent stage, we're taking pictures, and the rover is comparing the images it's seeing to an onboard map that it's carried. This map was generated from the orbiters that we have around Mars, and the same ones that we use to take the landing site. And on that map, we've marked out where are maybe some of the more dangerous places. And as the rover, as it's coming down, it can compare where it's headed with that hazard map. And if it looks like it's going towards one of those hazards, we have a built-in capability. It's called the divert maneuver. Curiosity did this too. After we pull away from the back shell and the parachute, we don't want that falling on top of us when we land. So we had a built-in divert maneuver. We used those engines to just go off in a direction. Curiosity, it wasn't a guided thing or a decision. It was just go in a particular direction. For us, we're able to use that same divert maneuver, and if it looks like we're headed to a more hazardous location, use that to go towards a safer location. So those are the two big new things that we have going on with our descent and landing. And definitely for those of our viewers, if you haven't seen it, I recommend searching for either 7 Minutes of Terror or Curiosity Landing. Watch the animated video that animations of the landing, but it's coupled with the team as that is actually happening with Curiosity landed. It's very exciting because you're going from, once you hit the top of the atmosphere, you're going about 13,000 miles an hour. You're hypersonic. And then when you pull that chute, that's a supersonic parachute, that slows you down to about 1,000 miles per hour. Then you slow down using the descent stage, getting down to 200 miles an hour. And finally, we're only going about 1 meter a second, or 1 mile, a little over 1 mile an hour, when we gently set down that rover on the surface.
That's amazing. And I'd be remiss if I didn't mention the Aerojet Rocketdyne thrusters being used on the Sky Crane to lower it down.
Yeah, thank you. Thank you for providing those.
You're welcome. You know, I'm just going to highlight the propulsion throughout the mission. So now that we've safely landed on Mars, Katie, let's talk about the science. And you already talked a little bit about how you remotely operate, but what's your first thing you're going to do once we safely land on Mars?
Well, we're all going to heave a big sigh of relief and then let out a major cheer. But then, you know, we get down to business. And George mentioned the terrain relative navigation. And I just wanted to mention that, you know, that capability and the enhanced computer that allows Perseverance and Mars 2020 to do that terrain relative navigation is actually, we're taking advantage of that on the surface as well. And so we're using that faster, better computer processing to actually be able to traverse autonomously in a way that previous rovers have not been able to. So we think we can cover more ground every day with Perseverance than perhaps Curiosity ever was able to do, because we're basically with the rover surveying our landing site as we, you know, our terrain in front of us as we drive, and the computer is making decisions about where to drive. And so that's an exciting new capability that we have thanks to this better processing power that is also benefiting our entry, descent, and landing. But if we think about what we're doing on the surface, I mean, so we'll have hopefully our science mission plan in mind. So the minute we find out where we've landed, that'll all kick into high gear. So we'll think, okay, where did we land in this site? Do we, you know, what do we want to do here at this location? And where are we headed next? Of course, during the early days of the mission, we're doing a series of instrument checkouts and checking to make sure that our systems are operating nominally, and we come online piecemeal. So slowly we add capabilities every day. So the science team during this period of time is really focused on coming up with that science plan. And as we test out our instruments, we'll be selecting targets. And this is something that we do on other rovers. And we say, okay, well, we have this much time today. And we're using this instrument. Let's identify the most compelling scientific targets, and we put a plan together. And of course, there's lots of deliberation that happens while we do that. The scientists talk about what is most scientifically compelling, and then we talk to the engineers. And sometimes the engineers will say, sorry, can't do that. It's too dangerous, or we can't reach it. And then we have to go back in conference and say, okay, well, maybe we'll change our plan, or nope, we really want this rock. Can you get it for us? And so that kind of back and forth is one of the things that makes working on a rover mission, you know, so fun, I think, for so many people, is this working together as a team and doing that back and forth and give and take as you take hundreds of people to operate a single robot on another planet. And so it's a really unique experience that we have, and one that is very satisfying every day when you can come to a consensus about what to do on the surface, and then actually you get that data back. And so we'll be focused on that, you know, getting through those early days of Mars time when we're living on the Martian clock instead of the Earth clock. And those are, you know, those are fun, but kind of stressful days when you're walking around like a zombie sometimes because you're sleepy. But we do our best to make good decisions for the rover during that time, and that time is really essential to take full advantage of all the time that the rover has awake on the surface of Mars before we take our own human considerations back into account. So eventually we will transition off of Mars time. But then during that time, you know, that's when we are getting excited for our first sampling opportunity. We have ambitious sampling goals with this mission, and so we know that we have to get going, putting together that sample cache, because we hope that we have a rendezvous a couple years down the line with the next leg of Mars sample return. So we've got to get going, and we've got to do the science and collect the samples that will enable the next leg of that campaign. So we'll be thinking about that as soon as we get on the surface, and doing our best to plot a course and collect a suite of samples that will really feed, I think, generations of scientists when those samples come back. So we feel the responsibility, but we're excited to have that responsibility, knowing the potential for what it sets up in the future.
Oh, that's wonderful. So I know we're at the top of the hour. The panelists have agreed that they can stay longer, but and so we're going to talk a little bit about future Mars exploration, and then we'll get to more Q&A from the audience. But I just want to let folks know who did have somewhere to go that the panelists are going to stay. So let's move in. You mentioned the sampling. So Perseverance is collecting samples. So Neil, Lockheed's been a part of some previous sample return missions. And so can you talk a little bit about sample return missions and how you possibly could return samples from the Mars Perseverance rover?
Sure. So there's already RFIs in place for this next mission that you're talking about. It's going to be called Mars Sample Return. We recently completed a proposal for one of these RFIs to go off and build another aeroshell. This one, Mars 2020 aeroshell, was 4.5 meters in diameter. The next aeroshell for Mars Sample Return is going to be even bigger, believe it or not. It could be as big as 5 meters in diameter. So we were asked to propose this newer, bigger aeroshell. In addition, there's a new lander that's an even larger lander that's JPL will be responsible for. It's called the Sample Retriever Lander. And so this big lander has to get down to the surface, and its primary purpose is to go pick up the samples that Perseverance has left down on the surface. So the next mission to Mars will be close to where Perseverance is right now, so that they can go pick up those samples. And then there will be additional missions that actually land a rocket down on the surface of Mars that could be used to take those tubes, stainless steel tubes that have samples from Perseverance, and fly those back to the US, or back to the world, the Earth, so that we can see what's actually down there on Mars and see if there's any signs of life. But those are missions out in the future. This particular RFI we just proposed to would launch in 2026. So we're talking about 4 or 5 years out. And then at the sample return mission is probably a year or two after that. So
great.
We're hoping to be part of all those. We love Mars, and we love going there whenever we have an opportunity.
Well, you have that in common with Aerojet Rocketdyne. We love Mars too. So going to turn to George and just see, George, do you have any other additional thoughts on sample return missions? And then if not, what kind of planning is going on for future Mars robotic science missions?
Now, since Neil brought up the fact that there will be future missions that will need to go return these samples. We, Mars 2020, cannot lift off and come back home. And one thing that's very unique, I talked about the prior missions, and we kept building on prior missions and the knowledge. Each mission we've done has, taken the knowledge from prior ones and built on that. But this will be one of the first time where we've actually had hardware interfacing between 2 different missions launching in 2 very different opportunities. And so I want to illustrate kind of what that interface will be. So since I'm at home, I didn't have my usual props of my 3D printed sample tubes, but I realized that a little flashlight is about the same size as a sample tube. I even took my calipers to it, and it just so happens that this is roughly the same size and shape, even this little bulbous end of a sample tube. So we're carrying about 42 of these with us, and we'll be able to leave them on the surface. And so the future missions that we're talking about designing, we've already been working for the past several years creating what we call interface control documents. So basically agreements between our mission and future missions to be on, are there any requirements we have to actually place on these tubes, and how we can keep the samples, keep sample integrity for when we eventually get them home. And what do those future missions, how do they need to be designed to actually pick these things up and put them in some sort of container to come home. And continuing our flashlight analogy, the actual sample itself, it turns out it's pretty close to the size of a AA battery, maybe one and a half AA batteries. And so that's what we're talking about. This is going to be the goal that we get home. And if you can go to chart number 21, I actually have a picture of the real sample tube. This is part of our caching system. This is during thermal vacuum testing of it. And what we're doing in this image, what is happening, we're testing, putting the tubes in and out of their storage silos that we have to carry. We're able to, once the sample is in the tube, we have to bring it inside the rover, seal it up with a hermetic seal, a cap, and then we have two choices. We can either hang on to it for a bit and wait until we want to drop it, or we could drop it right there. Most likely our plan is we're going to be putting them back in the silos where we pull them out. And then once we get to a location on the surface where we want to place this set of samples to await the future missions, then we would start depositing them there. We call that the depot cache approach. So all these future missions that we're starting to look at is we're in the planning stages now. And a big component of that is doing it with our partners in the European Space Agency. So some of the elements that Neil talked about, the retrieval landing system, landing a rocket, we call it the Mars Ascent Vehicle, that would lift off the set of samples, would be provided by, we're looking for being provided by NASA. European Space Agency is interested in providing what we call the fetch rover, such that if Perseverance itself isn't able to deliver the samples to that lander, a fetch rover, a smaller thing that's specially designed to go and pick up these types of tubes and bring it back to the Mars Ascent Vehicle. And then once it gets off the surface, there needs to be a return orbiter. And that's the third component of this, sort of three major components: the sampling mission, that's us; a retrieval mission on the surface, get it off into Martian orbit; and then another mission that will rendezvous with that sample container that's in orbit around Mars and bring it home to Earth.
Wow, that's amazing. Thank you so much for sharing that and bringing your flashlight to explain it to us.
Oh, I got a new prop now. It's great.
Great. All right. So, Katie, as I mentioned earlier, I've got this great exploration rocket NASA does. It's the Space Launch System that wants to bring humans to Mars. So from your perspective, the science perspective, what needs to happen before humans go to Mars?
I think going to Mars is kind of like planning a trip here on Earth. You don't go without having done a little bit of research about what the location is like and what the conditions are like, and perhaps what you need to bring with you and what you can get when you're there. And so in some ways, it's very similar to planning trips here, but in particular, we want to understand what kind of conditions our astronauts or Marstronauts would experience if they went to the surface of Mars. And we've been making progress on that question with previous missions as well. And in particular, one of the concerns that we have for astronauts when they're out in that space environment is radiation. And there's an instrument on the Curiosity rover called RAD, which has been measuring radiation since it was on its journey to Mars. And so we know a lot about from previous rovers. But with Perseverance, we have a weather station basically to understand pressure, temperature, humidity, dust in the atmosphere. And those are all very important pieces of information we would want to know if we were to send astronauts to Mars, to know what kind of environment they would be encountering and what kind of equipment they would need, how their spacesuits need to be built. And so our robotic explorers are doing some of that reconnaissance and data collection that can help enable planning for human exploration. Another thing we often think about is the in situ resources that Mars might have that astronauts could take advantage of when they're on the surface and perhaps don't have to bring with them, because mass equals dollars in a lot of in a sense when it comes to missions like this. And so if there are ways we can take advantage of the resources that Mars has, we don't have to bring those things with us. So we think about things like understanding the climate cycle and understanding water and where it is at the surface or a subsurface and ice and what conditions, what the weather's like, to affect things like where those resources might be. And so those are the kinds of things that we think about and we want to understand, and what the material properties are of even the soils and the rocks are on Mars, because those could all be different resources that get used by astronauts in situ on Mars. So I think those are some of the things that we think about and that Perseverance in particular can contribute towards. And so each time we send a robotic explorer, we're making progress towards that goal of sending humans to Mars. And we can do that, fortunately, in a way that addresses interesting science questions for Mars about Mars's atmosphere today and the conditions on Mars, while also, in service to that goal of human exploration and advancing that part of our objective.
I love the sustainable approach that you all are really taking to exploration and taking it one step at a time. I think it's great, and I commend you for that. So before we get into the lightning round of questions, because we've got a lot coming at us, I wanted to ask Neil one thing about, he mentioned the Dragonfly that he's working on, which is going to send like a drone-like vehicle to Saturn's Titan moon. And so I wanted to know if you could talk about the lessons learned from the Mars 2020 Perseverance rover and the Mars 2020 program, and how you're applying that to the Dragonfly mission, Neil.
Sure. So we're always gathering lessons learned from the various programs that we work on. Started back, at least for these big Mars missions like MSL, Mars Science Laboratory, we had to build a very similar structure, identical structure, essentially, is considered to be build to print. So back on the MSL program, we actually built 2 heat shields instead of just one. We needed a second heat shield to do environments on, and that heat shield became a spare, which when we got on contract for Mars 2020, that piece of hardware was provided as government furnished equipment for us to save money on the Mars 2020 program and use that heat shield in addition to the new back shell that we had to build. Well, as it turns out, the biggest risk on the program for the aeroshell was that heat shield that was now 10 years old survived the static test. It had to go through testing just like any other piece of flight hardware to prove that it was capable of going to Mars again. And as it turns out, that heat shield was not adequately built to survive the new environment that was being imposed on it by Mars 2020, and we had a failure at that point. So we had to go back and figure out, well, what happened to that first heat shield? It was the first heat shield of its kind of that size. So we learned a lot. We figured out what went wrong with that first heat shield, and we fixed it for Mars 2020. So it's all information that will be used on this new mission called Dragonfly. Turns out Dragonfly wants a 4.5 meter aeroshell as well. So it's very applicable to use everything we learned on Mars 2020 and MSL on this new heat shield. We learned a lot about how to improve our processes, how to test the hardware early so you know that there's no issues with the hardware. We developed some new test approaches using IR thermography to look for disbonds of the structure. We did some testing by applying a film to the surface of the heat shield during the static test so we could monitor strain levels as you're applying more and more load to that structure. So that we've got tons of lessons learned. We've got a big long list. I've got the same people working on Dragonfly that worked on Mars 2020. So
that's wonderful.
Yeah.
All right, so we're going to go into lightning round where we're going to try to ask as many questions as we can and answer them as quickly as we can. So Christopher asked, what's the launch system? So I'm going to go ahead and answer that one for you. It's ULA's Atlas V rocket. Ashley wants to know, you said it uses nuclear power. Is that the type that converts nuclear directly to electricity? George, do you want to take that one?
Yeah, we use what's called a radioisotope thermoelectric generator, and we use the exact same type that MSL used. And the basic technology has been used for U.S. space missions for decades, for 50 years. And in fact, Dragonfly, we use a similar system. And what it does is you have a small pellets of radioactive material, plutonium dioxide. It's a ceramic material that just heat. And we have several of those stacked up, and we have thermocouples wrapped around it. So it's a passive system. There's no moving parts. And those thermocouples directly convert that natural heat from radioactive decay into electricity. And for Perseverance, we get actually a twofer with the system. We don't, in addition to the electrical power, we also get the heat, which is what we need on the surface of Mars. So there is actually a fluid loop pumping through the rover to help transfer some of the waste heat from the RTG into the interior, what we call the warm electronics box, to keep the insides of Perseverance nice and warm. And that's what enables us to do what we need to do on the surface of Mars.
Awesome. And I'll also mention Aerojet Rocketdyne builds the nuclear power source for
that's right, you do.
The rover. So another Ashley wants to know, how long does it take to build a rocket? I think that's going to probably be best answered by the rocket provider, ULA, United Launch Alliance. So since we don't have them on this panel, I recommend if you go to their Twitter account and tweet them, I think it's at ULA Launch, they probably will answer that question for you. So next question from Joel. What opportunities might there be for citizen scientists to participate in the mission? Katie, is that something you want to tackle for us?
Yeah, you know, we've thought about different opportunities, and there are some opportunities already to do Mars research and assist with Mars research. And so citizen science, I think, is a growing area. We don't have anything at the moment that we have planned, but we're thinking about it in terms of thinking about identifying interesting places in the landing ellipse and perhaps, you know, opening that up and allowing, you know, our own community to take a look at the landing site and dig into the images and perhaps help us identify interesting locations. So we don't have anything that I can say that we've confirmed that we're going to do, but we're thinking about it, and we'll be sure to let you all know if we are able to kick something off like that. That's a great idea.
That's awesome. All right, so next question, George, this might be one for you, for Mario. Why are the wheels covered?
Oh, from the picture. Actually, if you can put one of those pictures of the rover with the wheel coverings. One of the, we're searching for potential evidence of ancient Martian life, right? Well, the first thing you don't want to do is bring some sort of Earth life with you and have our science instruments basically detecting Earth life. So one of the key things all Mars missions have done, this is part of what we call planetary protection, is, and that's why when you see these spacecraft being put together, they're in clean rooms to keep any potential of Earth contaminants as few as possible off the rover. So since the wheels themselves are what's going to be touching the surface of Mars, we want to keep them as clean as possible right up to the last minute. Katie, is there anything else you want to add to that, or did I hit it?
No, I think you hit it. I mean, we take it very seriously, the cleanliness of the rover and the system. because we want to make sure that the samples we get back, and the things that we find in those samples are indigenous to Mars and not things we've brought with us. And so we take that very seriously for this mission, particularly because of the sample return component. And so we've taken extra measures to keep the spacecraft clean and to protect our, what we call the sample intimate hardware, the parts of the rover that are going to interact directly with the samples. And so the wheel coverings are one example of ways that we try to keep the rover and the spacecraft clean as we're putting it all together and getting it ready for launch.
So the tires are a big question. So Patrick wants to know, how are the tires different on Perseverance opposed to Curiosity?
I can take that. So as some of you may have noticed, Curiosity is starting to get some holes in its tires. And this was not completely expected. And we, of course, we're doing a lot of things very heritage, trying to do as much build to print as we can. But even though the wheels are still, even though the part of the wheels have some holes in them, they're still perfectly capable and functioning. Curiosity can keep doing its mission for a long time. But we certainly thought that we'd like to maybe make some improvements. So what we did a test with various different types of sizes, size modifications to the wheels, also changes to the treads, because actually the tread shape on Curiosity is sort of a jagged chevron pattern. Turns out that actually is part of what was contributing to some of the holes. As we would roll across a particular rock, it would create greater forces there than it was designed. Oh yeah, thank you for putting that up. You can see on the Curiosity wheel that jagged, what we call the grouser. So for Perseverance, what we've done is we've made the skin, oh, perfect. You'll see the skin of the wheel, it's still all the same material. It's all hogged out of a single chunk of aluminum, but it's slightly thicker, so it's more robust. But once you do that, you're adding weight, right? So how can you potentially offset that? So we've made the wheels slightly narrower. We also made them slightly larger in diameter. And then we changed the tread pattern there. We now have sort of a curvy wave sign. And it turns out that these wheels are actually much more robust. We have a test set up at the Mars Yard at Jet Propulsion Lab, where we've run these wheels around and around and around, tens and tens and tens of kilometers, and they are just scuffed. So they're going to be quite durable for us. And on top of that, the new grousers actually give us a little bit better traction, so that we have a little bit more margin and a little bit more robust capability for going up or down slopes and sandy terrain.
Oh, that's awesome. All right, so we're going to move on to our next question. How, if at all, is COVID-19 threatening the July launch? And this is coming from Julie. And then what preparation activities, if any, have been moved to a virtual environment?
I addressed that a little bit earlier, but I'll repeat. Certainly the COVID-19 situation, like many people around the world, had to adjust to the way we do work, particularly for our folks who are doing the mission critical work. The majority of our team has successfully transitioned to remote teleworking. Timing helped in this regard. Most of our hardware was completed and already at the Cape, and had already been transported there. So with the small teams that we still do need to have working on the hands-on critical hardware, like I said, we've kept the first priority is the safety of the team, as well as the community they're in. So we've been able to work with occupational health officials at our NASA centers, and taking guidance from Centers for Disease Control, as well as the local centers there at Jet Propulsion Lab in Kennedy, and been able to put in place practices so that our team can operate safely. And so far, we've been very successful. We are still on target for launch, so still making the milestones.
Awesome. Sunny wants to know, Katie, will Perseverance provide data to students, community, or universities for research?
Yeah, so all of the rover data goes out almost as soon as it gets back. And we have agreements to make sure that the rover data that we collect is available and accessible by the public. And so, for instance, the images that the rover takes, those are, again, available almost immediately once they come down. In terms of some of the other data sets that we have, usually they take a little bit of processing and preparation, but then they get posted, particularly on the, it's the PDS is what it's called. It's a data repository, and we have an agreement to post the data there to the PDS. It's usually about kind of a 3 to 6 month time frame from the time that we get it. It's packaged with the proper files and explanation and put on the PDS, this data repository. And so yes, we make that data available to the public, and we encourage and are excited for those outside of the rover team to dig into that data and present science results and interpretations from that data.
Awesome. All right, I know we have just a little bit of time left. So Saita wants to know, should NASA collaborate with other international space agencies for Mars exploration like it does with the International Space Station?
I'll take that one. We absolutely do. In the game of space, we all can accomplish more if we're working together. Perseverance itself certainly has international contributions. If you can go to which one? There's the chart of the rover showing the instruments. Yeah, you'll see there's a couple of flags here. We have several contributions.